Welcome guys. So this is the section 2.1 problem set of the decimal number system, and here we have to find that what is the weight of 7 in each of the following decimal numbers. So we are given here some decimal numbers, and here we have to find that what is the weight of the 7 in each and every number. Okay, so first of all what we have to do, let me start A, and in A we can see that this is 1947 and by default the base here is 10. Okay, so when this is 10 we can see that while dividing it into the base elements we can see that here we have 7, 4, 9 and 1. Okay, so the base here is basically 10, so multiplying each element here with this base here, okay, so that would be 10 and that would be 10 as well. Okay, after it what we have to do, I have to write the powers of these 10 and these will start from this right side. So from right side I have to start from 0, 1, 2 and 3 and putting plus sign here in between them. Okay, so that is the number which I have here, and from simplifying them I can see that here I will get 7 plus 40. Okay, or let me not write it 40 first, so it would be 4 into 10 to the power 1 plus 9 into 10 to the power 2, which is the 100th, and 1 into 10 to the power 3. So that is basically, or I can write here 1 as well. So that is now the number here which I have divided into its elements. So we can very easily see that the weight of 7 in this number is basically, here I can see that the base weight of 7 is basically 1. So that is the answer of my part here. Okay, similarly in part B of my question, let me again proceed to part B of my question, and again writing this 7, 99, 10. Okay, proceeding it in the same manner. What I will get here, I will get here 9, 9, 7 and then 1. Okay, multiplying them with 10, 10, 10 and then 10. This is the standard procedure. Okay, and after it what I have to do, I have to start it from 0, 1, 2, 3, adding them together. Okay, and then simplifying them, I will get 9 into 1 plus 9 into 10 plus 7 into 100 plus 1 into 1000. Okay, so from it I can see that the weight of 7 is basically 100. Okay, so the weight of 7 is now 100, and it is now clear from this procedure. Proceeding to the third one here, or part C, let me solve it here. So that is now 1979, 1979, writing the base element here, and after it what I have to do, that would be 9, 7, 9 and 1. Okay, multiplying it with the base. Okay, here, and then proceeding it by writing the values of the power. So 0, 1, 2, 3. So it is very easy to see that all the powers will start from 0 and will end at the n minus 1. Okay, where n will be the total number of digits in my number. So adding them together here, I will get this one. Similarly, now simplifying it, I will get 9 into 1 plus 7 multiplied by 10 plus 9 multiplied by 100 and plus 1 multiplied by 1000. Okay, here we can see that this is the 7 and I have to find the weight of the 7. So weight of 7 is 10 here. Okay. So, in each of our questions we have found that here the weight of this 7 is 1, here the weight of this 7 is 100, while here the weight of 7 is 10, and these are the answers. Okay. So, we have calculated it by using the method which I have explained in this video. So, thank you so much, and I will see you with some more questions like this one. Hello guys. So, this is question number 2 of our section 2.1 of decimal numbers, and here we have to express each of the following decimal numbers as a power of 10. Okay. So, let us see the procedure that how to represent them as a power of 10. So, initially I have this number which is 1000. So, how to represent it? So, you have to see that whatever the number is, whatever the number of zeros here are, first of all you have to write the 10. Okay. After writing 10, what you have to do, you have to write the number of zeros available in each number here as a power of this 10. Okay. So, we can see here that here we have 1000, and for representing it, first of all I have to write 10, and after it I have to count the number of zeros here. So, this is 1, 2 and 3. So, I have 3 zeros here. So, that is why I will write here 10 raised to power 3, which is equivalent to the 1000. Okay. So, whatever it is, first of all you have to write the 10, which is the base element here, because now here we have this 1000 with the base 10. So, first of all you have to write this base here. Okay. This is the base, and after it with the base you have to write the number of zeros which are available in my number. Okay. If you want to represent it as a power of 10. Now, in part B of my question, here I have, first of all this is, I can see that this is with the base 10. So, writing this 10 here first. Okay. And what will be the power of this 10? So, let me count the number of zeros here. So, this will be 1, 2, 3, 4, 5, 6 and 7. So, I have 7 number of zeros here. So, this is 10 raised to power 7. That is the answer of part B. In part C of my question, again this is with the base of 10, and writing the answer of this question, first of all let me write the base which is 10 here, and after it let me count the number of zeros. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, there are 9 number of zeros, and I do not have to include this one with it. So, therefore, I will write 10 raised to power 9 with this. Okay. So, that is the answer of part 2 of the section 2.1, in which we have seen that how to represent any numbers which is composed of many number of zeros as a power of the 10. Okay. So, that is it for today, and I will see you soon. Hello guys. So, in this question we have to give the value of each digit in the following decimal numbers. Okay. So, here we are given 3 numbers. So, in these numbers we have to give the value of each digit. So, in order to do it, what we have to do, so let me start from our first number, that is 263. So, as this is a decimal number, so the base here will be 10. Okay. So, what we have to do here, first of all I am going to use the same procedure which I have used in question number 1 of this section. So, let me first divide it into the numbers. So, 2, 6 and 3, and after it let me multiply it with the base. So, base is 10 here. Okay. So, this is base, and after it what we have to do, we have to start from 0, 1 and 2 and then add them. So, these are basically the numbers which are here, and what we have to do, we have to give the value of each digit in the following decimal numbers. So, value of each digit will be here, simplifying them here. So, 3 multiplied by 1 plus 6 multiplied by 10 and plus 2 multiplied by 100. Okay. So, it will be from here this will be 3. Okay, let me write it in black. So this will be 3, and here 6 multiplied by 10 is how much? This is 60, and this will be here. So let me write them. So it will be 60 and plus 200. Okay, so these are the values of different digits in my number here. So these are basically for 2 this is 200, for 6 this is 60, and for 3 this is 3 as well. Okay, because of this procedure which I have used here. Okay, so from it we have seen that these are 260 and 3. Similarly, now for part B of my question, let me use it here. So part B, 5 4 3 6, okay, with the base 10. Okay, so now let me again use the same procedure here. It will be 5 4 3 and 6. After it, multiplying it with the base, this 10, this 10, and then after it 0 1 2 3, adding them together. Okay, and what will happen here? This will be 6 into 10 power 0 is 1, so 1 here, plus 3 into 10 power 1 is 10 here, so 3 into 10 plus 10 power 2 is 100 and multiplied by 4, so 100 here, and here 10 power 3 is 1000, so 5 into 10 power 3. Okay, so now here again similar method will be used here, where this will be 6, it will be 30, it will be 400, and here it will be 5000. Okay, so here this one is here, this is here, this is here, while this one is here. Okay, so that is the answer of part B of my question. Okay, similarly, now proceeding to the part C. Okay, so first let me write their values. So 2 3 4 5 4 3, and this is the decimal number. Now let me solve it. So here it will be 2 3 4 5 4 3. Okay, so after it, let me multiply each and every element or every digit here with 10 or the base of this number. So that will be 10 10 and 10. Okay, so after it I have to write the values of the power. So 0 1 2 3 4 and 5. Okay, then adding them together here, so this is the number. Now simplifying them, I will get 3 into 1 plus 4 into 10. Okay, 5 into 100. Okay, into 4 into 10 as power 3 is 1000. 3 into this is 10,000, and this is 2 into 1 lakh, which is 1 to 100,000. Okay, similarly, now simplifying them, it will be 3, it will be 40, 500 plus 4,000 plus 30,000, and this is now 100,000 or 1 lakh, which is 2 lakhs. Okay, so these are basically the values which are like this is this one, while this one. Okay, each and every value here. Okay, So these are different values for each and every element here. So 2 lakh is for 2, 30,000 is for 3, 4,000 is for 4, 500 for 5, 40 for 4 here, and 3 is for the third here. So that is the answer of part C of my question. So that is the end of my question, in which I have seen that how to find the value of each digit in the decimal number. Okay, so that's it for today, which is for your concept and how to represent different decimal numbers with their values as well. Okay, so thank you so much, and I will see you with some more examples, more interesting questions in our upcoming videos. Hello guys, so in this question we are asked to convert the following binary numbers to the decimal numbers. Okay, so the first question or the first part of this question is basically this one. So let me represent it with 0, 0, 1. Okay, and I have previously told you that all the numbers in any number system can be represented with this bracket and that number system as a subscript of the bracket. Okay, so this is basically 0, 0, 1, and this is the binary number. In order to represent this binary number in decimal number system, what we have to do, so let me first write all the digits which are in binary number here. So 0, 0 and 1. Okay, so these are all the numbers. After it, what we have to do, we have to take this base, okay, and we have to multiply it with every number here. Okay, so what we have to do, let me do it like this, representing it with this blue. So this 2, here 2, and here 2 as well. Okay, so now it is placed here. After it, what we have to do, we have to multiply it with every number, and after it we have to add them together. Okay, so here we have multiplied 2 with every bit here. So after it, what we have to do, we have to write the weights of all the 2's which we have written here. So let me start it from this right side, because here this one is the least significant bit, or will also call the LSB. Okay, so let me see here that here this is the LSB, okay, while this one is the most significant bit, or MSB. Okay, so least significant bit, least significant bit, while this one is the most significant bit in the binary number system. Okay, so let me write their weights here. So let me start it from 0. At the right hand side, or at the rightmost here, we have the LSB. So starting from 0, so this is 0, the second 2 is the weight of this is 1, and the last one, or the MSB, as the total number of bits here are 3, so it will be 2. Okay, so now let me calculate them. So 2 0, that is 1, and 2 raised power 0 is 1 as well. Similarly, this is 0 multiplied by 2, 1 is 2, so 0 multiplied by 2, and similarly 2 to 4, 4 multiplied by 0. Okay, so writing them here, 1 1 is 1 plus 0 plus 0, because everything multiplied by 0 is 0. So now here we will get what? We will get 1. So this is 1, and this is in decimal number system. So that is basically the binary to decimal conversion of a number. So this is part A of our question. Similarly, in part B, let me start solving it. So this is 0 1 0, again representing it with this 2 in the base. So after it, 0 1 and 0. Okay, multiplying it with 2, again the same procedure. Okay, and what we have to do, we have to then add them, and this is 0 1 2 weights of all the 2's here. So now calculating them, this will be 0, okay, this will be 2 2 2 1 2 is 2, and this is again 0 because anything multiplied by 0 is 0. So this will be now 2 raised power 10. Okay. Similarly 2 to the base 10. Okay. So that is the decimal number of 010. Similarly in part C we have 101. This is again in binary, writing them like 101, okay, multiplying it with 2. Okay. So the basic operation here is to write the exponents of all the 2's. So starting from 0, 1, 2 and them adding them. Okay. So it will be 1 multiplied by 1 plus 0 multiplied by 2 plus 1 multiplied by 4. So it will be 1 plus 0 plus 4. So this will be what? This will be here 5. So 5 in base 10. Okay. So that is the decimal equivalent of 101. So this is all about the three parts. Similarly in part E of our question, 1010. Okay. So now again 1010. Now multiplying it with 2, because this is a base in binary number system. Okay. And then 0 1 2 3 and then at the end adding them. Okay. Now let me calculate them. 0 multiplied by 1 plus 1 multiplied by 2 plus 0 multiplied by 4 plus 1 multiplied by 8. Okay. So here it will be 8 plus 0 plus 2 plus 0 and it will be 10 in decimal number system. So 10 is basically the decimal equivalent of 1010. In part F of our question, this is 1011. 1011 in binary number system. So 1011 and multiplying it with 2. Okay. Again the same procedure which we have been following, adding them and writing the exponents of this 2. So here 1 multiplied by 8 plus 0 multiplied by 4 plus 1 multiplied by 2 plus 1 multiplied by 1. Okay. So this will be 1 plus 2 plus 0 plus 8. So we will get what it would be. So 8 plus 2 plus 1 is 11 in the base 10. So that is the decimal equivalent of 1011. So the last one here is this one G, which is 1110. 1110 to the base 2. So writing it again 1 1 1 and 0. Okay. Now multiplying with it 2. Okay. And then writing the exponents 0 1 2 3, adding them together, and here 0 multiplied by 1 plus 1 multiplied by 2 plus 1 multiplied by 4 plus 1 multiplied by 8. So here we will get 8 plus 4 plus 2 plus 0. So ultimately we will get here 14 with the base of 10. Okay, so that is the equivalent decimal number of our binary number, which is mentioned in G here. Okay, so that's it for today, in which we have discussed the binary to decimal number conversion. With the other videos, I will see you very soon. Thank you so much, and I will see you soon. Welcome back, guys. So this is question number 7 of our book, and today we are going to encounter some more binary numbers, which are basically the fractional binary numbers. Okay, so you may see that here all the binary numbers also consist of this dot, which is in this case is called the binary point. Okay, so you may have seen different dots or the decimal points in the decimal number system, like 25.78 or 6.23 or so on. So this point here is basically, or this full stop is the decimal point here in the decimal number system. But here, as we are in the binary number system, so this is the binary point. Okay, so today we are going to see that how to convert these type of numbers into the decimal number. So let us get started. So let me first remove it, and let me first start my number, which is 110011.11. Okay, so now how to solve it? So here we have this binary point. Okay, so let me write it here. So it will be here, this will be here. So after it, let me write all the numbers as I used to do with the conventional numbers. Okay, so this is 1 after it, and this is 1 here as well. Similarly here, this one, okay, then 00, and then 11. So these are basically the numbers which are in my question here, and that is basically the binary number. So now again writing 2 with each of 1 here, so multiplying 2 with it, okay, 2 with it as well, 2 and 2. Okay, similarly with them as well. Okay, let me first write the exponents with all these two bases. So at the left side of my binary point, I have all the numbers. So let me write the exponents which are starting from 0, 1, 2, 3, 4 and 5. Okay, so these are all the exponents, and we have to add them then. Okay, so I have added them. So after calculating it, I will get the whole number out of this binary combination. So what to do with this number? Okay, so what, as we can see that here we have a 0. So let me draw a picture like this one here. So this is the midpoint, which is 0. So here in this line I have 1, 2, 3 up to any positive number, but here at the right side I will have -1, -2, -3 and so on. Okay, so keeping in mind the same thing or the same line here, let me use the same concept here, and here I will start writing the exponents of the base from -1 and then to -2, and then I have to add them together unless and until I will get back to the end of my numbers here. Okay, so in this way I will get this combination. Okay, so let me simplify them. So simplifying them, this will be 1 into 2 raised to power 0 is 1. Okay, similarly 2 multiplied by 1. Okay, 0 multiplied by 4. Okay, this is 8, and 8 multiplied by 0. Similarly this is 16 multiplied by 1, and this is 32 multiplied by 1. Okay, what to do with it? This is now my binary point, and here 2 raised to power minus 1 is 1 into 1 over 2. Okay, similarly this is 1 multiplied by 1 over 2 raised to power 2, which is 4. Okay, now let me simplify it some more here. So it will be what? This will be 1 plus 2. Okay, these two will cancel out because anything multiplied by 0 will be 0. So 0 0 here, so 0 plus 0. Okay, similarly 16 and 32 here. Okay, what about these? So 1 by 2 is 0.5, so 1 multiplied by 0.5 is 0.5. Okay, so and similarly 1 by 4 is 0.25. So adding it with 1 multiplied by 0.25 is this one. So this will be like this one. Now adding them together, this binary point will be here. So 0.5 plus 0.25 is, how much is this? This is 0.75. Okay, and what to do? This is the decimal point, and adding them here. Okay, what it will happen? So 16 plus 32 is 48. 48 plus 2 is 50, and this is 51. So ultimately I will get, adding this with this one, so I will get 51.75. Okay, so that is the decimal number, and that is the answer of my part A of this question. So it is about the conversion of the fractional binary numbers to the fractional decimal numbers. Okay, so here we have a point which is called the decimal point, but the same point here we had in our binary numbers, and that was basically the binary point. Okay, so that's it for part A. Similarly, in order to start the part B here, let me write this 101010.01. Okay, so part B here 101010.01, okay, or 0.01, and that is, yes, the same one here, and that is the binary number here. So now using the same concept here as we have applied in our previous question, so what to do? So using 1 0 1 0 1 0, and then this binary point, and then 0 and 1. Okay, after what we have to do, we have to write or multiply 2 with every bit here. Okay, so bit is basically the binary digit, and as this is a binary number, so each and every digit here is basically the bit here. So that is basically the binary digit. Okay, similarly 2 with it and with it as well. Okay, did I multiply it here? Yes, this one. So now what we have to do, after we have to write the exponents. So here this is first, so 0 1 2 3 4 5, and here it will be -1 -2. Okay, adding them together, the same procedure which we have previously followed. Okay, now simplifying it, let me simplify it. So this is 0 point, and that would be what? This is 0 multiplied by anything would be 0, and similarly what it would be? So 1 multiplied by 2 power -2 is 1 by 4. Okay, similarly it would be 0 plus 1 multiplied by 2 is 2. Okay, so 0 again. 2 raised to power 3 is 8, multiplied by 1 is 8. 2 raised to power 4 is 16, multiplied by 0 is 0. Okay, 2 raised to power 5 is 32, 32 multiplied by 1 is 32. So this would be 32 plus 8 is 40, and 2 is 42. So it would be 42. Okay, 42.1 by 4 is 0.25. So it will be here 25. Okay, so now this is my decimal number. Okay, so here we can very easily see that by using or by deploying all the previously established steps, we have converted our number into the binary number, which we can see here. Okay, other questions are similar as that of this one, so I suggest you guys to use other parts of this question for your own practice, but let me give you a hint here, because here we have this question in which all the terms here are 0 except our this one and this one here, while all the bits at the right side of my binary point are 1. So what is this? So this is basically 2 raised to the power 0, and this is 1 2 3 4 5 6, this is 2 raised to the power 6. Okay, so only 1 into 2 raised to the power 6 plus 1 into 2 raised to the power 0, these are the only numbers which will be here, because all the other numbers will be multiplied with 0 and will be nullified. Okay, similarly here it would be 1 by 2 plus 1 by 4 plus 1 by 8. Okay, so now let me simplify them. So 2 raised to the power 6 is basically 64. 64 multiplied by 1 is 64, plus this one is 2 raised to the power 0 is 1, so this is 1. Okay, similarly 1 by 2 plus 1 by 4 plus 1 by 8, so 1 by 2 is how much? That is 0.5 plus 0.25, and this is 0.125. Okay, so adding them together, I will get 0.5 plus 0.25 is 0.75. Okay, and that would be 0.125 with 0.75 will be how much? This would be 0.875. Okay, so now adding this 65, because 64 plus 1 is 65. So here from this question I will get what? I will get here 65.875. Okay, so that would be the decimal number of it out of this binary number, and that is one of the easiest possible way in which I have told you how to calculate the decimal number from a given binary numbers. Okay, from the same method you can use the other parts of this question for your own practice. I am not going to solve them in this video, but in other videos I will definitely give them a try. So with this exercise problem, I am leaving you with all the other parts of this question, which are D, E, F, G, H. So I hope you will practice all of those things, and if you encounter any difficulty in these questions, so let me know in the comment section, and I will see you with some more question in our upcoming video. Thank you so much, and I see you soon. Hello again. So in this question we have to find out that what is the highest decimal number that can be represented by each of the following numbers of binary digits or bits. Okay, so here we have these numbers, and we have to know that if we have 2, 3, 4, 5, 6 or any number of bits, so what is the highest number or in decimal which is represented by those number of bits. Okay, so in order to find the highest decimal number, okay, so let me use here highest decimal number from a binary, from bits, from certain number of bits, and those bits, let me call them certain number of bits, let me call those bits as n. So their value can be here 2 raised to the power n minus 1. Okay, why minus 1? Because in every bit or in any binary number, all the number starts from 0 0. Okay, just like in our combination or in 2 bits number which starts from 0 1 2 3. So 0 0 0 1 1 0 and 1 1. We can see that the highest number it can represent is basically 3, but if these are 2 bits, so putting 2 raised to the power n, if we put 2 n here, what will we get? 2 2 is 4. So basically 2n shows the quantity of the numbers which can be represented by the number of bits, while this 2n minus 1 shows the highest decimal number from the n number of bits. Okay, so that is basically the scenario, and from it we can calculate that if we have part A, so here we have 2 bits. Okay, so the highest number here would be 2 raised to power 2 minus 1. So 2 to 4 and 4 minus 1 is 3. So 3 is the highest number here, while the total number of decimal numbers here will be 4. Okay, so 4 numbers will be represented, and those numbers will be 0, 1, 2 and 3, while 3 is the highest number. Okay, so that is the concept behind these type of questions. Let me solve part B of my question. So here we have 3. Okay, so 3 will be 2 raised to power 3 minus 1. So this would be 8 minus 1. 7 is the highest number which can be represented, while 0 to 7 will be 8 numbers which can be represented by 3 number of bits. Similarly, in C we have 4. Okay, so 2 raised to power 4 minus 1, 2 raised to power 4 is 16 minus 1. So that would be the 15. 15 is the highest number which is represented by 4 bits. Similarly, D, if we have 5. Okay, so 2 raised to power 5 minus 1. So this is 32 minus 1, or it will be 31. Okay, so that is the highest decimal number which can be represented by this 5 bits. Okay, similarly, any of the combination or any number of bits can be used here. Let me put or take 8 here. So this is G. So from 8 I will get 2 raised to power 8 minus 1. Okay, so it will be how much? So let me use the calculator here. Okay, 2 raised to power 8. So 256 total numbers can be represented by 8 bits, while the highest number here will be, okay, so this would be 256 minus 1 and it will be 255. Okay, so the highest decimal number here will be 255. Similarly, I here we have 10. Okay, so 2 raised to power 10 minus 1. So let me use here again 2 raised to power 10. So it will be 1024. 1024 minus 1. Okay, or 1023 is the highest decimal number which can be represented by 10 bits. Okay, so the same concept will be used in each and every part of this question, but the main formula or the main thing here is this formula here. Okay, where this 2 of n, what is this? This basically shows, let me write it with this, right? This 2 of n shows the total number of decimal numbers represented by n bits. Okay, but while by subtracting 1 from it, I will get the highest decimal number from those n number of bits. Okay, so I think that's it for today, and I will see you with some more interesting questions which will be related to the number systems in our upcoming videos. Thank you so much, and I will see you soon. Hello again. So another very interesting question in which we are asked to find the number of bits which are required to represent the following decimal numbers. Okay, so this is one of the very important question which is very hard for the new guys in the field of digital systems to find that how many bits will be required to represent a certain decimal number. Okay, so how I do it, how I approach these type of problems. So let me first discuss that methodology first. So the first number here is this 5. So how would I approach these type of problems? So if I have 1 bit, if I have 2 bits, 3 bits, 4, 5, 6 or 7 bits. Okay, so these are the bits here. Okay, and the maximum decimal number which these can represent will be the, here it will be, with 1 bit the maximum number I can get is 1. With 2 bits the maximum number is 3. With 3 bits the maximum number is 7. With 4 I have 15. With 5 I have 31. With 6 I have 63, and with 7 I have 127. Okay, these are basically the bits, and these are basically the maximum numbers which can be represented by those number of bits. Okay, so suppose when I will have this 5 here, so I can very easily see that there is no 5 here, there is no match between them, but I already know that this 3 is the maximum number which can be represented with 2 bits, while this 7 is the maximum number which can be represented by 3. So this 5 will somehow lie here. Okay, so this will be the number which will be between 3 and 7, and I know that there is never any binary point in between the bits. Okay, I have to show that how many bits, so that would be the maximum limit with which this 5 can be represented. Okay, so from this formulation I can very easily see that this will be the maximum point here, because these 2 bits cannot represent this 5. So 3 will be the number with which my 5 can be, this 5 is a decimal number which can be represented with 3 bits. Okay, so that is the method which I use. So similarly here you may also ask me that how I calculated these one. So in previous video I will also share the link of that video here. So I have showed you that it was basically 2 n minus 1. So if you put n equal to 2, okay, so this is n here. So if you put n equal to 5 here, so it will be 2 raised to the power 5 is 32 minus 1 is 31. Okay, so in this manner I have calculated all these things. Similarly, systematically, how would I calculate the value of the bits which can represent this 5? So in my formulation I can see that here it can be written this 5 like this one, where n are the required number of bits which are used to represent this 5 which is in decimal number. Okay, so how to find out this n here? So I can very easily show you that this can be found out by using the log 2 of 5. Okay, so if you will find it, you will calculate it, you will get some number. So you have to round that number up to the highest term. Okay, so suppose if you got 1.2, so this means this is almost equivalent to 2. So 2 bits will be used to represent that number. Similarly, if that is 3.7, so it means that is 4, because bit is a whole number, bit is basically the whole entity. So therefore you have to round that off to the higher value, or this is called the roof rounding off. Okay, so that is here. So in order to calculate the number of bits for this 5, what you have to do, you have to calculate n log of 2 of 5, but if you see the calculator, there is no log of 2, always you will get log of 10. So what do you have to do? If you want to calculate log of 2 of any number, and you don't have the log of 2, so what you have to do, you have to use the log of 10 of that number and divide it over the log 10 of 2. Okay, so here first of all let me calculate log 10 of 2. So here log 10 of 2, this is by default 10 log. Okay, so here it will be 0.3, so 0.3. Okay, so it will be used here very seldom, that's why I have calculated it. And log 10 of 5 is how much? this is 0.698. 0.698. Okay, so now dividing it over 0.3, what I will get? I will get 2.3 here. Okay, but 2.3 cannot be a whole number, it cannot be the number of bits. So if I round it off to 2 here, so what I will get? I will get 2 bits, but the maximum decimal number which I can get from 2 bits is basically 3, so it is not possible. So therefore I have told you that always you have to round it off to the higher number. So 2.3, if this is 2.3, you have to round it off to 3. So 5, if this is 5, it will be represented by 3 bits. So n will be equal to 3 for this 5 decimal number. Okay, so these are basically the two methods which are used for the calculation of the number of bits. Okay, similarly for part B of my question, here I have 10 to the base 10. Okay, the same method I can very easily told you that with 2 bits the maximum number I can get is 3, with 3 bits I can get 7, with 4 bits I can get 15. So you will see that this is the range, and in this range it will lie. So therefore 4 bits will be used for this number, but as I am going to use the formulation or mathematical formulation here, so n will be equal to log of 10 of 10 divided by log 10 of 2. So this log 10, I have known that this will be 1, log 10 of 10 is 1. Okay, so let me prove it here as well. Okay, that is 1, because if you want to find the log of any number, what does it mean? So suppose you have a number 2 raised to power 3 equal to 8. Okay, so that is 8, but if you have a number like 2 of n equal to 16, so you want to find out the value of n, which should be the number here. So you can very easily see that this is 4, but how to find it mathematically? For it you use log 2 of 16 equal to n. Okay, so that is the methodology for which log is used. Similarly, if you want to calculate it for log of 10 100, okay, equal to n. Okay, so what does it mean? It means that if the power of 10 is n and you got 100, so what will be the value of n? So it can be very easily seen that n will be equal to 2 here, because that is the required value of n, which will give me 100 when n will be the power of 10. Okay, I can also use it here and you will see that it conforms to my answer here. So here log of 100 is how much? That would be 2. Okay, so that is the essence of this logarithm here. Similarly, what if I want to find the value of n here? So let me calculate them. So this is already found out, and that is 0.3. So log 10 of 10 is 1, because the what should be the power of 10? That I will get this 10 here, so that is 1. Okay, so if I will use log of 10, it will be 1. Let me use it here again. Okay, so 1 by 3 or 1 by 0.3 is how much? That is 3.33. Okay, so as I have already stated that this cannot be rounded off to the lower value, so therefore whenever I have something with the decimal point here, so I have to round it to the highest value. So the highest value here is 4, so I can see that 4 bits are required. This is n equal to 4. These are required to represent this 10 here. Okay, so that is for the 10 here. Similarly, what if I want to see that how many bits should be used to represent this 15? So I can very easily see that this 15 is already mentioned here, that 4 bits are used to represent the 15 here. Similarly, in order to do it, I can also use the same formulation which I have had here. So 15 with the base 10, for it the n will be log of 10 of 15 divided by log 10 of 2, that is already known, and that is 0.3. So let me calculate it. log of 15, okay, and divided by 0.3, what I will get, this is 3.92, okay, this, which is when rounded off I will get 4, okay. So 4 bits are used to represent this 15. This is also a very important question for all of you to know, that how many bits are used for any numbers to be represented. Similarly for D you can see that it lies here, so it is already known that the value it will have will be 5 bits. Similarly you can use the same formula here, okay. So 5 bits will be used here. Now let me pick this H, okay. Now let me use this H, and H is 160 decimal. So how many number of bits should I have to represent this one? So now let me use the same formulation which I have. So with 7 bits the maximum number I can get is 127, and with 8 bits, if I have 8 bits, the maximum number I will get here would be 255. So it lies here in between them. So I have told you that if the range is here known, the lower number and the highest number within which the number can lie, so I have to pick the highest number, okay. So 8 bits can be used to represent this 160, okay. So 8 bits will be used. So now let me use my formulation here which I have made. So 160 divided by 0.3, okay. So now it will be log of 160 divided by 0.3. So how much would it be? This is 7.3, 7.34. So again, rounding it off to the higher number, I will get n equal to 8, okay. So 8 is the number of bits which can be used to represent this 160, okay. So that is all about the question, or the very important question, that how many bits are required for any decimal numbers to be represented in the binary numbers, okay, or in binary digits. So that's it for today, in which we have discussed all the things here, and I have also shared a very simplified trick here which I use in my mind to abruptly tell that how many bits can be used to represent that decimal number. So that's it for today, and I hope you have got all the idea that how to represent these numbers. Thank you so much, and I will see you. Welcome back, guys. So today we are going to discuss the decimal to binary conversion, and in this regard we are going to solve question number 11 of section 2.3, in which we have to convert each decimal number mentioned here to binary by using the sum of weight method, okay. So what is basically the sum of weight method? So let me first use the part A of my questions here. So that is in decimal, okay. So basically I know that in all the weights, when I convert the decimal number into the binary one, so I have different weights. So those weights basically starts from 0, and those are basically the powers of 2. So that start from 0, then 1, 2, 3, 4, 5, 6, 7, okay. So these are different weights and their values. If I calculate their values, so let me calculate their values. So the value of 2 of 0 is, let me have it 1, this is 2, this is 4, this is 8, 16, 32, 64 and 128. Similarly, if I have this 2 raised to power 8, so it will be how much? 2 raised to power 8 is, sorry, I have used the blue color here, so that is now 256. 6. Okay. So, these are different weights. In order to convert my decimal number into the binary one, I have to use these weights in addition. Okay. So, using in decimal to binary conversion by using the sum of weight method, what we have to do, if we have a decimal number, let me call 12. So, I have to search for the highest possible number here, which basically matches my decimal number here. Okay. So, what is that highest possible number out of these three? So, this is basically this 8. So, let me select this 8 and write 1 with it. Okay. So, with 8, what are the other lowest possible numbers which can be, when added to 8, will give me this 12. So, that is clearly this 4. So, when I will write 1 with it, the others 2 will become 0. So, therefore, this is the binary number which is equivalent to my number here, because when these will be added together, okay, so what will happen? So, when this 8 multiplied by 1, when I will have 8 multiplied by 1, 4 multiplied by 1, 2 multiplied by 0 and 1 multiplied by 0, and when I will add them together, what I will get? I will get here 12 in the decimal number system. So, therefore, this 110 is the equivalent, 1100 is the equivalent binary number for this 1210. Okay. So, that is the procedure for which I have to use this table. Okay. So, this was my part A. Similarly, in order to solve part B of my question, what is that? That is 15. Okay. So, that is now 15 in decimal. So, what is the rule of thumb? What you have to do? You have to search for the highest possible number which matches my number here. Okay. So, that is 15. So, what is the highest possible number? So, highest possible number again is this 8. Okay. So, let me write 1 with it. Okay. Similarly, what is the second number when added with 8 will give me the closest possible number with 15. So, that is again 4. So, 8 plus 4 is 12. Okay. What are the other numbers? This 2 is when added, and this 1 will be added because 8 plus 4 is 12. So, plus 3 will give me this 15. So, 2 plus 1 will also give me 3. So, therefore, selecting both of them, I will get what? I will get 15 here. So, it will be the binary equivalent of it will be 1 1 1 1. So, that is the binary equivalent. So, similarly, using the same procedure which I have previously used, like that 8 multiplied by 1 plus 4 multiplied by 1 plus 2 multiplied by 1 and plus 1 multiplied by 1, what I will get? I will ultimately get this 15. Okay. Similarly, the other question, let me first clear it. The other question now, part C of my question is 25. 25 in decimal, what is the possible equivalent binary number? So, what is the nearest highest number here? So, 32 is higher than 25. So, let me select this 16. Okay. So, how much is left now? So, 25 minus 16 is 9. Okay. So, now then selecting this 8 out of 9. So, now 16 plus 8 is 24, and now 1 is left. So, selecting this one here while others are 0 0. So, that is what, that is my 25, because 16 multiplied by 1 16 plus 8 is 24 and multiplied by 1 will be 25. So, the binary equivalent of 25 is 1 1 0 0 1, this 2. Okay. So, that is the binary number. So, I think you have got the concept that how can we convert any decimal number into the binary one by using the sum of weights method. Similarly, if I have another number here, let me use here this D, and that is 50 in decimal. Okay. So, what is the highest possible number here? That is now 16. Okay. How much is left now? 18 is left, because 50 minus 32 is 18. So, that 16 again. So, out of 18 I have got the 16. 16 plus 32 is 48. So, 2 is left. So, selecting this one and making others 0. So, that is the binary equivalent of 15, and it will be equal to 1 1 0 0 1 0, and that is in binary. Okay. Now, E, part E is 65 in decimal. So the highest possible number here is this 64, and 64 plus 1 is 65, while others are now zeros. Okay, so this is 1 and 1 2 3 4 5 zeros, so therefore it will be 1 1 2 3 4 5 and this one. So that is what, that is the binary equivalent of 65. So 1 2 3 4 5, yes, that is the correct one. Okay, so part E. Similarly, part F. What is part F? So part F contains 97 in binary, in decimal, sorry. So therefore now the highest possible number here is again 64. So 97 minus 64 is how much? That is 33. Okay, so now using this 32, so it would be 64 plus 32 will be 96, and this one 97. So all others will be 0 now. Okay, so now again it will be 11 4 zeros and 1 in binary. Okay, similarly part G. In part G of my question, what is this? That is 127 in decimal. So let me first remove it. So for 127 in decimal, what is the highest possible number? That is again 64. So 64 I have got. So 64 plus 32 is how much? That is 96. So 127 minus 96 is 31. So again now for 31, let me use this one here as well. So that would be 16 plus 64 is how much? That is 80. 80 plus 32 is 112. 8 is 120. 120 plus 4 is 124. This 126 and then 127. Okay, so that is now 127 and all the 7 bits which are ones. So let me use it here. So 1 2 3 4 5 6 7, all ones are basically the binary number here. Okay, so that is the binary equivalent of what? That is 127. Similarly, the last one here, and that is now 198. Okay, that is 198 in decimal. So I have to find the binary equivalent of this number. So what is the highest possible number? The highest possible number here is this 128. Okay, so with 128, when I will add 64, what it will be? So 64 plus 128 is 130. 130 and 62 is 192. So it will be 192. How much is remaining? 6 is remaining. Okay, so 192 plus 4 is 196, and 196 and this 2 is 198. Okay, so that is now 0 0 sorry 0 0 0. So that is now the binary equivalent of it are 1 1 triple 0, okay, 1 1 and 0. So that is what? That is the binary equivalent of 198. So that's it for today, in which we have discussed a table here, and you have to draw it because these are all the powers of 2's, and because I have to use the sum of weights methods, so it is mandatory to first draw this table, and then you can very easily convert any decimal number into the binary one. Okay, so that's it for today. I will see you with more interesting questions in our upcoming videos. So if you did not subscribe my channel yet, please subscribe it and like this video. Thank you so much, and I will see you soon. Welcome back, guys. So this is question number 12 of our book, in which we are asked to convert each decimal fraction to binary using the sum of weights method. Okay, so if you recall, previously we have converted our decimal numbers to the binary numbers by using the sum of weights method, but here this question is different from that of the previous one because it contains the decimal number which is mentioned here. Okay, so in order to solve these type of questions here, what we have to do, so if you recall again, so previously what we have done, we had the power of 2's which were the multiplicative factors with our binary numbers, and what we had to do, we had started it from 0, then 1, then 2, okay, and up to some power of 8. Okay, so these were basically the power of 2's which were the multiplicative factors, and if we had any number in decimal, we have to select any of these power of 2's by multiplying them with 1 or zeros. Okay, so the overall procedure were mentioned in that question, and the link of that video is now I am attaching with this video. Okay, similarly, what happens if we have the decimal point here? So in that case, I will have the binary point in my binary numbers here. So in order to do it, what we will do, we will again use the power of 2's, but now the power of 2's will start from -1, then -2, -3 up to the higher term until and unless I want to find out the corrected version of my fractional binary number. Okay, so this was basically the introduction, and we can very easily see that if this is basically the 0 point, so here this is now, if these are the numbers, so here the powers will start from 1, 2, 3, 4 up to infinity, while here the powers will be from -1, -2, -3 up to the infinity. Okay, so here in order to do it, what we have to do, we are going to solve our questions as we have solved our previous questions. So here what we have to do, we have to start it from the binary point, then 2 raised to the power -1, 2 raised to the power -2, 2 raised to the power -3, okay, 2 raised to the power -4, 2 raised to the power -5, 2 raised to the power -6. Okay, so these are basically the powers of 2. So let me calculate them. So 2 raised to the power -1 is 0.5. Okay, so let me call it 0.5. This is 0.25. Okay, this is 0.125. This is 0.0625. Okay, this is now 0.0312, and this one is, okay, this one is how much? This is 0.0156. Okay, so what we have to do, again the same procedure will be followed here. Suppose if we have a number which is now, let me have here part A, and in part A what we have to find out, we have here the 0.26 in decimal number. Okay, and we have to find the equivalent binary number. So what it would be, so first of all let me select the highest possible number which I can select from here. So let me start from here. So it cannot be 0.5 because 0.26 is lower than 0.5. So let me make it 0. Okay, so multiplicative factor of 0.5 will be 0. Similarly with 0.25, yes, it can be included because 0.26 is greater than this. So let me include it. So how much is now left? If I subtract 0.25 from this 0.26, how much is left? That would be 0.01. So therefore this is now 0 because 0.15 is how much? That is now greater than what? If I 0.26 subtracted from it this 0.25, okay, so I will have 0.01. Okay, so I have to select this, so that if it will be added with 0.25, I will get 0.26. So therefore this number is greater than 0.01, so it is not included. Similarly this is not included, and similarly it is as well. So this one is the only possibility which I can include here, so this can be included here. Okay, so now I will get these numbers. So this is basically the binary number here. So let me use it. So it will be 0.01 0.01001. Okay, so that is the binary number. Okay, so how it would be calculated? Again, using the same procedure which we had previously used. So these two will be multiplied together. Okay, these two will be multiplied together. So here I will get 0, here 0.25, here 0 as well, 0 0, and here 0.0156. so these will be added at the end, and you will see that their summation will be almost equal to 0.2656. Okay, because this is almost, if I want to get the correct answer up to the required number of decimal points, I have to move it to the higher number of binary numbers. So now I am stopping it here. So there it is now almost equivalent to the 0.26. Okay, so that's why I have calculated this number, and this is the procedure I can use to find the binary number from the decimal fraction number. Okay, so this is part A of my question. Okay, similarly, in order to solve the part B of my question, this is 0.762. so let me 0.762. so this is now here 0.762 in decimal, and the binary equivalent of it will be, let me remove it from here. So now let me see that if I had, what was that number? So 0.762. so 0.5 can be included here. This is lower than 0.762, so it can also be included here. Okay, so I will get 0.5 here. Okay, so what is the next procedure here? I have to subtract this 0.5 from 0.762. so 0.5 is here, so I will get 0.262. Okay, so now I have to see that whether the next number is greater than this one or lower than this. So it is lower than this one, so let me include it as well. Okay, so when it is included, let me subtract it from this number. So 0.25, so it will be 0.012. Okay, so now this is 0.012, and I have to select the next number, which is now which should be smaller than or equal to this one. Okay, so this is not the smaller or equal to this one, so that's why I'll make it 0. This is also the same case, this is the same case, while this one is almost equivalent to this one, so therefore I am going to select it. Okay, so that's why this is now the binary number, and when the same procedure will be applied here, like multiplying the lower terms with the higher terms here and then adding them together. Okay, what I will get? I will almost get the number which is mentioned here. So now, okay, so now let me remove it. Okay, and the number which I have got here is basically 1100001. Okay, so that is my binary number. Okay, so that is, as this is 1100001, so I also have to write this binary point with it as well. Okay, so if you want to make it more concise, so include this 0 with it as well. Okay, so that is the binary equivalent of 0.762. this is part B. Similarly, now in order to solve this, what I have to do, let me solve it here as well. So here you will see that this is 0.0975. so let me use blue color for it. So what I have to select, let me solve it on the fly. So this will be included, and with it we can very easily see that this one will also be included, because adding them together I will almost get the 0.09. okay, and I am getting this point from these two digits, so therefore it will be how much? These two will be 0 0, this will be 1 1. okay, so I will get how much? This number will be 0.0975. this is part C, 0.0975 in decimal, it will be equal to 0.00 0 1 1 in binary number. Okay, so that's it for today, in which we have seen that how to calculate or convert each decimal fraction to binary using the sum of weights method. Although this is one of the lengthiest and very complex method, but it is mostly used by the practitioners who are fluent or has practiced binary to decimal or decimal to binary conversions frequently. Okay, so that's why we have also discussed this method as well, and from the next lecture we are going to talk about the division method for converting our decimal number to the binary ones. Okay, so that's it for today. If you have any questions, you can ask me in the comment section. Thank you so much, and I will see you soon. So another very important video in which we are going to convert each of the decimal numbers here to binary number by using the repeated division by 2. Okay, so what is basically this method? Let us start solving our questions, and in solving it you will get to know that what is meant by repeated division by 2. Okay, so the first part of my question is here 13. Okay, that is basically in decimal, and I want to see that what is the binary equivalent of this number. So what we have to do, we have to write this number here, and I have to divide it over what I have to divide it over 2 repeatedly. Okay, so let me first divide it. So dividing it over 2, what I will get, so 2 multiplied by 6 is 12. So when 12 is here, 1 will be the remainder, and that remainder will be here. Okay, so that is the remainder of the first division. Okay, what is next? As this is the repeated division, again I have to divide it over 2. So when it is divided over 2, I will get 3. Okay, so when I will get 3, the remainder of it will be 0. Okay, similarly I have to divide it over 2 again, and I have to divide it over the number which is 2 until and unless I get 1 here. Okay, so now again dividing 3 over 2, what I will get? I will get 1, and the remainder of it will also be 1. Okay, so what is basically the procedure here, how I will write them here? So you can see that these are the numbers. Okay, so I have to write my binary numbers which will be started from here up to this one, while this one will be the MSB. Okay, and this one will be the LSB. Okay, so now writing it over here, what I will write, I will get here 1 1 0 1. Okay, so that is basically my binary number. Okay, so that is the binary equivalent of 13, and I can also check it here as well, that if I have 1 0 1 1. Okay, so this is now 2 0 2 1 2 2 and 2 3, multiplying them together. Okay, and then adding them, what I will get, it will be 8 plus 4. Okay, plus 0 plus 1. So what it will be, this is now decimal 13. So it proves that our method is correct, and the binary equivalent of 13 is 1101. Okay, so that is for the part A of my question. I am not going to solve each and every question here today, but I am going to tell you the procedure, that what is the fundamental procedure of repeated division by 2 to convert my decimal numbers into the binary one. Okay, so this was basically the first part. Now let me solve part C of my question. Part C is 23 in decimal, and what will be the binary equivalent of it? Let me use the same procedure here. Okay, here this is 23, this is 2, I have to divide it over 8. So here I will get 11 with the 1 remainder. Okay, similarly here dividing it over 2, I will get here 5 with the 1 remainder. Okay, similarly again dividing it over 2, I will get 2 with the 1 remainder. Okay, and at the end I will get 1 with the 0 remainder. Okay, so that is basically 1 0 triple 1 is the binary equivalent, and I have to start it from here up to here, okay, while this one is the MSB, while this one will be the LSB. Okay, let me write it here again. This is for your understanding. So now let me write it here. What I will get, this one will be 1 0 and 111 in binary equivalent. So these numbers are, this will be here while this one is here, okay, this one is here, this is here, while the last one is here. So these are basically the numbers which I have represented here. So this is basically the decimal to binary conversion. Now let me solve E here. Okay, so let me solve part E of my question. So what is part E? So part E is 35. Okay, so part E is 35 in decimal. Okay, so converting it into the binary here, what I will have to do using the same procedure here. So 35 dividing it over 2, what I will get here, I will get 17 with the 1 remainder. Okay, similarly 2 here, what I will get here, 8 with the 1 remainder. Okay, again 2 4 with the 0 remainder. Okay, 2 2 with the 0 remainder, and at the end what I will get, 2 1 with the 0 remainder. Okay, so now again I have got these numbers. So it is again from here to here, and the binary numbers I will get here will be 1 000 11. This is the binary equivalent of this number, where this one is here. Okay, this is now here, and so on. Okay, because this one is now here, and all the numbers will remain here. Okay, so that's it for today, in which we have converted some parts of my question. And if you have any difficulty in solving any of the question here, please let me know in the comment section, and I hope all the conceptual of the questions is now clear. If you have any difficulty, I will try to make another video regarding the questions here. So till then, take care of yourself, and I will see you soon. So in last lecture we have converted the whole decimal numbers into the binary numbers. So now we have here decimal fractions, and we have to convert them into the binary by using the repeated multiplication by 2. Okay, so what is the method of repeated multiplication by 2? Let me solve part A of my question, and that is 0.76. Okay, that is in decimal, and I have to see that what is the binary equivalent of it. So the first number here I have is the 0.76, and previously in converting our number to the binary one, I had to divide it over 2 repeatedly. Now I will multiply it with 2 unless and until I will get 1 out of it. So multiplying it with 2, what I will get, okay, so multiplying it with 2.76 multiplied by 2, what I will get, 0.76 multiplied by 2, I will get here 1.52. okay, so here I will get 1.52. okay, so what I will do here, from this 1.52, what I will get, I will take this 1 here and put it here. Okay, these will be the, this will be the remainders box. So taking it here, what I will get here, now when I will get 1 from it, what I will have now, I will have 0.52. okay, so I think it is clear now. What again I have to do, I have to multiply it with 2 again. So when I will multiply it with 2, what I will get here, I will get 1.04. okay, so now here you can see that again we have got 1 from here. So, okay, so taking it and putting it here again, this will be 1 1, and here when this is removed, what I will get, I will get here 0.04, and multiplying it with 2 again, what I will get here, 0.08. okay, so when I will get this here, I have no numbers at the left side of this decimal point. So therefore what I have to do, this is 0. okay, so therefore I will write 0 here. Okay, so here again I have this number and this is now again here, so writing here 0.08, okay, and multiplying it with 2, what I will get? I will get here 0.16. okay, so again what is here the number here? Again this is 0. okay, so taking it, writing it over here, and I will again get here what? This is now 0.06, and again taking it, writing it here 0.16 and multiplying it with what? Multiplying it with 2, what I will get? 0.32. okay, again the same procedure, because now again I have 0 here, so taking this 0, this is 0, okay, and writing it over here, this is now again 0. okay, again here this is 0.32. okay, 0.32 multiplying it with 2, what I will get here? This is, let me denote it with this black color here as well, with black color. So here I will get 0.64, here I have the 0. okay, so what I will get here as this is 0, here again I will get 0. So this process will be repeated unless and until here from the multiplication of a number with 2 I get 1, a whole number. okay. So this will take a lot of steps, therefore I am not going to more steps here. So therefore the number or the binary equivalent of 0.676 is 0. Here this one 1100 up to the 4 binary points. This is the number and this is the binary equivalent of my number, where the whole overall procedure is listed here. okay. So that is for the part A. Similarly for part B of my question, here I have 0.56 in decimal. okay. So in order to do it, what I have to do? Again I have to use the same procedure which I have had here. So 0.456, let me do it here as well. So 0.456 multiplied by 2, what I will get here? So here 0.456 multiplied by 2, here this is 0.912. so here 0.912. okay, and the remainders which are here. okay, so the remainders are here, this is the remainder. So the remainder here, the first remainder is here 0. okay, similarly taking it and writing it here, so 0.912 multiplied by 2, here I will get what? Here it will be 0.912 multiplied by 2, here I will get 1.824, 1.824. okay. So 1 will be taken from it and here it will be put down. okay. So let me use the red color here. So here it will be, so that would be 1. So 1 will be removed from here. What will happen? It will be 0.824 multiplied by 2. okay. So again multiplying it with 0.824 multiplied by 2, what I will get here? 1.648, 1.648. okay, from 1 here again I am doing it directly, and when 1 will be removed it will be 0.648 multiplied by 2. okay. So here again, so that would be minus 1, it would be 0.648 multiplied by 2. So here it will be 1.296, 1.296. okay. So again from here 1, okay, and here 0.296 multiplied by 2, what I will get? Subtracting 1 from it, that is now this, and multiplying it with 2, what I will get 0.592. okay, so 0.592, 0 here, writing 0 here as well, okay, and doing it again, 0.592 multiplied by 2, okay. So what I will get here multiplied by 2, so it will be 1.184, taking it here and writing here, and it will be repeated, and unless and until here I get 1.00, okay. So that's why now here I am writing it here. So up to the 4 binary points here I will have 0.1110, okay, and that is the binary equivalent of my number, which is 0.456, okay. So that's it for today, in which I have solved first two parts in order to give you an idea that how decimal fractions can be converted to the binary numbers. So it's the end. That's it for today, and I will see you with some more questions in our upcoming video. Thank you so much, and I will see you soon. So today we are going to start section 2.4, which is related to the binary arithmetic, and in this section we are going to discuss the addition, subtraction, multiplication and division, which is usually carried out with the readily available decimal numbers, okay. So we are going to see that how these operations are carried out in the binary numbers. So before doing the addition in our today's lecture, we are here to see some basic operations or fundamental additions which will be useful throughout in this lecture. So here we have to see that in order to adding any bits here, so first of all we have to see that 0 plus 1 is always equal to 1 plus 0, and that is equal to 1, okay. Similarly 1 plus 1 is always equal to what? That is in decimal 1 plus 1 is 2. So in binary this will be equal to what? 10, because 10 in decimal is equivalent to the 2, okay. Because now you will, when you will convert it, if this is in binary, and when you will convert it, it will be 2 in the decimal number system, okay. So I think it is clear. Similarly 1 plus 1 plus 1, this is in decimal is 3. So therefore in binary the binary equivalent of the 3 is what? That is 1 1, okay. So these operations or these additions should be clear in your mind before diving into the details of our questions. So after doing all this, what we have to do, let us start our part A, and here we have to add 1 0 with 1 0, okay. So let me add them. So 1 0 1 0, these two are the binary numbers, so I have to add them, okay. So adding them, what I will get, this is 0 0, here it will be 0, and 1 1. I have previously told you that 1 plus 1 is always equal to what? That is 1 0, okay. So that would be 1 0. So that is the binary number, okay, and the addition of 1 0 and 1 0 gave me 100, okay. So this is 2, this is 2 in decimal, this is 2, if you convert it, 1 0 is 2. Similarly this one is also 2. So when you will add them, you will get 4. Why? Because now you can see that this 100 is the binary equivalent of this 4, which is in the decimal number, okay. So I think it is clear now. Similarly, in order to solve part B of my question, this is 1 0 with 1 1. So let me add them. So 1 0 with 1 1, adding them, what I will get? 0 plus 1 is here. I have done it already. So this is 1 plus 0 is 1, and 1 1 is also equal to what? That is what? That is 1 0. So 1 0 1 1 is what? That is the binary equivalent or the summation of 1 0 and 1 1, okay. Now similarly, so adding 100 with 1 so where should I have to write them? Because now here I have 3 bits, here I have 2 bits. So you have to keep in your mind that whenever you are given the number of bits which are lower than the other quantity here, so what you have to do, you have to start writing them from the LSB. Okay, so that is basically the lower significant bit, so you have to start writing it from, so that is here 1 and here 1 as well. Okay, so now let me add them, and when I will add them, this will be 0 plus 1 is 1, because here as well this 0 plus 1 is 1, and what is here is, as there is nothing here, so I have to write 0 here by myself, and 1 plus 0 is 1. Okay, so 1 1 1 is basically the output of my addition here. Okay, I have added them. Similarly, in part D of my question, what is part D? This is 111 and 101, so 111 and 101. Okay, adding them, what I will get, 1 plus 1 is how much? I have done it here, that is what, 10. So I have to write 0 here, and 1 will be carried here as the carry bit. Okay, so that is the carry bit. So now I have to add them, add 3 of them, so 1 plus 1 plus 0, this is how much? Again this is 1 0, because this is now 2. So now writing 0 here, and again will be 1 will be the carry bit here. Now you can see that there are 3 ones, 1 1 1, and I have earlier told you that the summation of the 3 bits will be equivalent to 3 in decimal, which is equal to 1 1. So now writing 1 1 here, that is basically the summation of 111 and 101. Okay, so that is for my part D. So part E is, let me write it here. So here it will be 1 1 1 1, 4 bits here, while this one here I have 3 bits. So this, following the same procedure which I have followed in our part C. Okay, so writing them from the LSB. Okay, and the last bit here, making it 0 by myself. So now here 1 1 is how much? That is 0, and here it is 1. Okay, now again 1 plus 1 1 is 1 1. Okay, so there it will be 1 will be carried here. So 1 plus 1 plus 1 is again 1 here, and 1 is also the carry bit here, and 1 plus 1 plus 0 is how much? That is 1 0. So that would be 0 1. Okay, so that is the summation of these 2 bits. Okay, the last one here is for your own practice. Add it, and you will see that addition is not that much difficult as you were thinking about it. So that's it for today, in which we have seen that how to add 2 or more binary numbers by using the binary arithmetic procedure for the binary numbers. So that's it for today, and I will see you with some more interesting questions in our coming videos. Thank you so much. See you soon. So question 16 of the section 2.4, in which I have to perform the binary number subtraction. Okay, so what is the procedure here? So the part first of my question is here 1 0, and from it I have to subtract 1. Okay, so in binary this one is basically 0 1. So that is basically the 1, but how to subtract them? Here you have to keep in mind some very important stuff, and that is, once you will have to subtract this from here. So you can see that here the higher number is 0. So 0 from 0 I cannot subtract 1. So therefore I have to take carry from the number which is at the left hand side. Okay, so what will happen if I will get carry from it? This 1 0 will become how much? This will be now 2. Okay, so from 2 and 1 will be subtracted, what will I get? I will get here 1. Okay, so that is basically the essence of overall procedure here. Similarly, if I will have this number here and I have to subtract something from it, what will happen? Here I can see that I cannot subtract 1 from the 0. So I have to take carry from the next item on my left side, but here this one is also 0. So therefore it will also look at its own left side. So therefore it will get what? It will get 1 carry from it. So I can see here that it will be 0 0. When it will get this carry from here, what will it become? It will become 1 0. Okay, so this is now 1 0 is how much? This is 2. Similarly, when it will give it to the right, what will happen? So this 1 0 when give carry to the right hand side bit, what will happen? It will not be like 0 will remain here and 1 will be shifted there. No, it cannot be like this, because now this number here is 2. So when it will give 1 to 8, okay, what will remain here? It will become 1, okay, because from 2 it will get 1 here, so 1 is left here. So that is the concept which you will be using here, okay. So let me start solving these questions, and with the passage of time you will get to know that how did I solve this question. So this part A of my question, here I have 0 again, and at the lower side here I have 1. So I cannot subtract 1 from the 0, so it has to take this carry here, okay. So when this will take carry here, it will become 1 0. So 1 0 is basically 2, okay. So from 2 I have to subtract 1, and therefore here I will get 1, okay. So when it has taken this 1 carry from the left hand side, what did I left here? So it was basically 0 here. 0 minus 0 is how much? This is now 0 as well, okay. So that is basically the subtraction here, in which I have subtracted 0 1 from this 1 0, and here I have got this 0 1, okay. That is the binary subtraction. Similarly, when I have to subtract 1 1 from this 1 0 0, what would happen here? The second scenario which I have covered here, you can see that here I have covered the scenario which is here. So how did I do it? So you can see that this is 0, and from it 1 cannot be subtracted, so therefore it will look into the left hand side bit. So it has to get carry from it. It cannot get carry from it because this is now again 0. So therefore it will ask the left hand side of its own. So therefore this is 1. When it will give it a carry, what will happen? This will become 1 0. 1 0 is 2, which is already mentioned here. So when this 1 0 will give 1 carry to 8, okay, because this is the required bit here. So this will become 2 now, while 1 will remain here because this was 2, and when this 2 will give 1 here, 1 will remain here, as we have discussed here in this question, okay. So therefore this is 1 1. So this is basically how much? This is when 1 will be given to 8, this will become 2. So 1 0 is 2, 2 minus 1 is this 1, okay. Similarly, how much is left here? This is 1, so 1 minus 1 is 0, while this is also 0 because this bit was carried from the right hand side bit. So this is now 0 0 1. So this is the result of the subtraction from these two numbers. Similarly, when I have to subtract this 1 0 0 from 1 1 0, what would happen? So let me write this 1 1 0 here and 1 0 0 here, and I have to subtract them. This 0 minus 0 is 0, this 1 0 0 is 1 0 subtracted from 1 is 1, and 1 1, and 1 subtracted from 1 is 0, okay. So that is the binary equivalent of this number, okay. So that is for this number. Similarly, part D of my question, this is basically a 4 bit number, and similarly here I have this 2 bit number, and I have previously told you that whenever I have the lower number of bits here, so what you have to do in the MSB, you have to write these zeros, okay. So now in order to subtract them, 1 will be subtracted from 1, this will give me 0, this will also give me 0, okay, this will be 1 and this will be 1 as well, okay. Similarly, part E of my question, 1 1 0 1, okay, and 1 0 1, again subtracting them, 1 minus 1 is 0 0, 1 minus 1 is 0, and here this one as well, okay. So that is the last question, and I have left it for your own practice. So in this question, what I have done, I have basically carried out the binary number subtraction, and you can see that it is now very easy to subtract one binary numbers from the other one if you have these two confusions which I have mentioned here clear in your mind, okay. So that's it for today, and I will see you with some more interesting questions in our upcoming videos. Thank you so much and see you soon. So question 17 of our book, in which we are asked to perform the binary multiplication over the numbers which are given here in different parts. Okay, so let us start part A. Okay, and here we have to multiply 1 with 1 0. So what we have to do, first of all, you have to write one number here while the other number beneath it. Okay, and you have to multiply them. What are the steps of multiplying them? Okay, what you have to do now, you have to take this first number and multiply it with first with this one, then with this one. Okay, similarly after it, what you have to do, you have to take this number, okay, and you have to multiply it with this one and then with this one as well. Okay, so in this way you will get some numbers which you have to add together, just like we used to do with the decimal numbers. Okay, so let me start it here. So in multiplying it, first multiplying this 0 with 1 here, so 0 multiplied by 1 is 0. Let me denote it with the red color. Similarly 0 multiplied by 1 is again 0. Okay, now this 1, and let me denote it with this green color. So multiplying this 1 with this one first. So first of all making here this one, and what does it mean? It means to make this space blank. Okay, so this space is blank and I am representing that blank space with the help of this cross. So now 1 multiplied by 1 is 1. Similarly 1 multiplied by this one is also 1. Okay, so this one is here. What we have to do, we will add them together. So as this cross is basically the blank space, so 0 will remain here. Okay, similarly here 0 plus 1 is 1, and similarly this space is again blank and blank space is considered at 0. So 1 plus 0 is 1 here again. Okay, so the product of these two numbers is 1 1 0. If you see that this 1 1 is basically 3, this 1 0 is what? This is 2. So their product is basically 6. So let me see whether this is 6 or not. So this is what? This is 2 to the power 0, 2 to the power 1, 2 to the power 2. Okay, so when these will be multiplied and added together, you will see that at the end, by adding them, this will be multiplied by 0. Okay, so at the end what you will get? You will get this 6 as well. So it means that our product is correct and the answer of in decimal number is 6, while in binary multiplication the answer is also consistent. Okay, so that's for part A of my question. Let me start it for part B of my question, and I'm going to do it directly. So starting it for 1 0 1, okay, and multiplying it with 1 1, what you have to do? You have to multiply them. So 1 multiplied by 1 will be 1, 1 0 0. Okay, 1 1 is 1. This one will be blank, so I have to start it from here. So this one will multiply, this one will be multiplied here. So 1 1 1, 1 0 0. Okay, and 1 1 will be 1. Okay, so now this one will remain here because this space is blank, so therefore it will be here. So 0 plus 1 is 1, this will be 1, and this one will also be 1. So that is the answer of these two. So what is it basically? So let me again check it. So 1 0 1 is how much? That is 2 1 0. So this these two terms will remain same. So this will be 4 plus 1 is 5. Okay, 5 multiplied by this one is 3. So it should be 15, and we will see that by converting this one into the decimal number, we will see that this is also 15. Okay, so it shows us that our multiplication is correct. Okay, so that is the product of these two numbers. Similarly, now let me start it for part C. Okay, so for part C, I can see that this is 1 1 1 and 1 1 0. So now I have three numbers. I have to multiply them by using the same procedure. So this 0 will be multiplied with these three, and I will get 0 0 0. The procedure will remain same. This will be the blank one, while this one when multiplied with 1, all the threes, I will get here 1 1 1. Okay, so whenever you will have a third bit here which you have to multiply with all the numbers, so here I have given it one space. So now in order to write the third product here, what I have to do, I have to give it the two spaces, okay, from the right side. So 1 multiplied by 1 will be 1. Okay, so I have to start it from here. Similarly here and here as well. Okay, so here I will get this one. So this one will be 0 now 0 plus 1 0, as this is blank, so here again this is 0. Okay, so 0 1 1 is how much? This is 2, so 0 and 1 will be carry here. Okay, so 1 1 1 is 1 1. Okay, and here this 1 1 is how much? This is 1 0. So that is basically the product of my two numbers which are given here. Okay, so that is for this number. Similarly, for part D of my question, what I have to do? Again, I have 1 1 0 0. Okay, and similarly 1 0 1. So multiplying it by using the same procedure, first of all this will be multiplied with the upper 4 bits. So what will happen? I will get 0 0 1 1. Okay, then this blank space, and the 0 will be multiplied with all the numbers, and I will get here zeros. Okay, 4 zeros, because the numbers here are 4. Similarly, the third bit, when multiplied with them, I have to give it 3 spaces. So this will be 1 0 0 1 0 0 1 1 1 and 1 1 1. Okay, so this will be the number. So 0 will be here, this 0 plus 0 is 0, 1 0 0 is 1, 1 0 0 is 1. Okay, this 0 plus 1 is 1, and this one here as well. Okay, so that is basically the binary equivalent of the product of my these two numbers. So the overall procedure will remain same for all the number of bits, but just you have to do that if the number of the bits will increase for the multiplying term. What you have to do in writing the product of those numbers here before addition, you have to give them space away from the previous bit. Okay, so the overall procedure will remain same for the part E and part F as well. So it is for your concept that how the multiplication of the two or more than two binary numbers can be performed. So that's it for today, and thank you so much for all your concentration, and I will see you with some more questions with some more interesting stuff in our upcoming videos. Hello guys, so this is section 2.5 which is related to the complements of the binary numbers. So the first question here is this question number 21, in which we have to determine the ones complement of all the parts which are given here. Okay, so what is basically the ones complement? So ones complement, let me have this number here, that is 100, and in order to find the ones complement of it, what we have to do, we just have to take the complement of each and every term here, and by taking the complements here, what will happen? All the zeros will be converted to the ones. This 0 will be converted to 1. Okay, similarly this 0 again will also be converted to what? This will also be converted to 1, while this is 1, and this 1 will be converted to 0, because the complement of 0 is what? Its complement is 1, while the complement of 1 is 0. Okay, so therefore the ones complement of 100 is 011. Okay, similarly, in order to find the ones complement of 111, what it would be? So it would be 000, because it will be the complement of each and every term here. Okay, similarly in part C it is 11100, so it would be 00 and 11, because each of the binary number here will be complemented and will be inversed, and if it is 0 it will be converted to 1, and if it is 1 it will be converted to 0, and vice versa. Similarly, let me solve this part E of my question, and it is now 100 10 10. Okay, so what will happen? 100 will be converted to the D011. Okay, this 10 will be 01, and this 10 will be 01 as well. Okay, so that is about the ones complement, which is also one of the very important concept in the complements of binary numbers. Similarly, another very important concept here is the 2's complement. Okay, so let us have the question 22 in which we have to determine the 2's complement of each binary number here. Okay, so again the same binary numbers are given here, and in order to find the 2's complement, what we have to do, in order to find the 2's complement of any number, first we have to find the 1's complement. Okay, just like here we have this part A. So we have, if a number we have is 1 1, so its 1's complement will be 0 0, and in part 2 of it, what we have to do, we have to add 1 with its 1's complement. Okay, so now here we have the 0 0, so in part B of my question, what we have to do, I have to add this 1 with it. Okay, so what I will get, I will get 0 and this will be 1. So what is this? This is basically the 2's complement. So this is also a very easy and very important method which we can use to convert or complement any binary number to its 2's complement. What are the benefits of 1's complement, 2's complement? We will discuss them in our upcoming videos when we will solve the relevant questions. Okay. Similarly, if we have a number here that is 110, okay, so its 2 complement, first of all we have to find the 1's complement. So 1's complement it has will be 0 0 1. Okay, this is 1's complement. Okay, and to find the 2's complement I have to add 1 with it. Okay, so what will happen, this is 1 1, so it will become 0 1, so it will be 1, and this is 0. So what is this? This is now the 2's complement. Okay. Similarly, our part C here is 1 0 1 0. Okay, so again the 1's complement of it is 0 1 0 1. Okay, that is the 1's complement, and in order to find the 2's complement I have to add with it this 1. Okay, so how much would it be? 1 1 is, this is 0 1 1 1 0. Okay, so that is what, that is the 2's complement. Okay, similarly now let us take another example here and let me solve it. So let me take the problem F here, that is 1 1 0 0 1, that is F 1 1 0 0 1. So in order to find the 2's complement of it, what we have to do, first of all find the 1's complement. So that would be 0 0 1 1 and 0. Okay, that is the 1's complement, and that, let me write it here as well, 1's complement. Okay, and in order to find the 2's complement, let me add this 1 with it, so it will become 1 1 1 0 0. So that is now what, that is the 2's complement. So that's it for today, in which we have discussed the fundamentals of 2's complement, 1's complement, and solved the exercise questions of our book by deploying that concept. So I think it's enough for today. You are encouraged to solve the other questions which I did not solve here, and these are left for your own practice. So if you have any question, you can ask me in the comment section. Take care of yourself, and I will see you soon. So today we are going to talk about the signed numbers, which is section 2.6 in our book. Okay, so before going to dive into the details of the signed numbers and solving the relevant questions, we have to see that what is meant by the signed numbers. Okay, so in previous sections we have seen that the unsigned numbers, Okay, if we had the unsigned decimal numbers, so those can be represented with the n number of bits, where n can have any number. So suppose if we have n equal to 3, so it will contain 2 raised power 3 means 8 numbers in binary. Okay, so 3 bits can represent 8 numbers in maximum in the binary numbers, which will be from 0 to 7. Okay, so you can see that all the numbers here are positive, which will range from 0 0 0 0 0 1 0 1 0, okay, and 0 1 1. Similarly 1 0 0 1 0 1 1 1 0, okay, and 1 1 1. So each number here is basically, this one is the 0 and this one is 7. So these are starting from 0 and ending up to 7. So the question rises here is that what if I want to represent the negative numbers with the same number of bits, what would happen here? So in order to do so, what has happened in the signed numbers is that the leftmost bit or the MSB has been assigned to the signed numbers. Okay, so this is the signed number, this is again the sign number bit. Okay, so what are these basically? So these are the bits used for sign. Okay, so what does it mean by sign? So if these are 0, so 0 means positive, and if it is 1, it means negative. Okay, so in order to do so, what has happened here? So these bits are used for sign. So therefore now if I want to represent different numbers by using these signed values, so here this will be 0. So all the numbers here with this 0 bit at the MSB would be the positive numbers, while all the ones here will basically denote the negative numbers. Okay, so here what would happen, that if we have the n number of bits, okay, so previously for the unsigned numbers, those started from 0 and ranged from 2 raised power n minus 1 number. So this was the range. So if n was 3, so the range was basically this one. If this was for n equal to 3, if n was equal to 2, okay, if n was equal to 2, what it was? So it was 0 to what? That was 0 to 3. If n was 4, that was from 0 to 15, and so on. Similarly, now for the signed numbers, what would happen? So the question here is that what would happen? So now the numbers will range from minus 2 raised power n minus 1 up to n minus 1 up to n minus this minus 1. So the range here will be this one. So this was the range for the number of bits in the signed numbers or the total number of binary numbers. So now if n equal to 2, so according to this formula, what would be the range? So the range here would be 2 raised power n minus 1 is this one, okay, up to 2 minus 1 up to 1. So it would be from minus 2 1 up to, okay, so it would be from minus 2 to how much? That would be from minus 2 to 1, which will also include 0 as well. Okay, so those would be minus 2 minus 1 0 and then 1 for the n equal to 2. Similarly, if we have the number of bits, if the number of bits here are 3, So these will range from -2, 3 minus 1 to 2, 3 minus 1 minus 1. Okay. So how much would it be? It would be -2 up to this one. So it would be -4 and here it would be 3. So the numbers here would be, here the numbers will be how much? Those would be -4, -3, -2, -1, 0 and also 1, 2, 3. So these are 1, 2, 3, 4, 5, 6, 7, 8, total 8 numbers, while here we also have these 4 negative numbers and also 4 positive numbers as well. Okay. So this formula is also a very important formula which shows you the number of binary numbers with the signed integers. Okay. So with this method we can represent any number by using the signed binary numbers, and let us solve some more examples related to this formula which will be helpful for converting any unsigned numbers to the signed numbers. So stay tuned. Welcome back guys. So this is question number 23 of section 2.6 related to the signed numbers, and here we have to express each decimal number in binary as an 8-bit signed magnitude number. Okay. So the first number here is this 29, that is the plus 29. So what we have to do, as this is positive, so as we have previously shown you that the MSB bit, which will be the 8-bit here, will be 0 in case it is positive, and if it was negative, okay, the bit the MS bit here or the leftmost bit was basically 1. Okay. So what we have to do, first of all, let me convert this one to the binary number or the 8-bit binary number here. So here we have 2, 0, 1, 2, 3, 4, 5, 6 and 7. Okay. So the conversion from decimal to binary is already covered in this series, and I will put the link of that video in the description box. So the first thing here will be this 16. Okay. 16 plus 8 will be 24. Okay. And 24 plus 4 will be 28. 28 plus 1 will be 29. Okay. So all the others will be 0. Okay. So now this one is the binary equivalent of 29. Okay. Let me now separate it out. So this will be how much? This is now plus 29. So as the bit here is 0, so it shows that it is a positive number, so therefore it will remain like this. So that is the binary equivalent of this plus 29. Similarly, the second number here is 85. So B 85, and that is the negative number. So first of all, let me find the binary equivalent of 85. So in order to do so, what I will have, this 2 raised to power 4 is 16, 16, 32, 32 is 64. So 64 here will, this will be now 1. Okay. 64, and how much is left now? 85 minus 64. So 85 minus 64 is now 1, and 21. 21 is left. So what I can get here, this one is now 1, this is 0. So here I will have 64, and this one is 2 raised to power 4 is 16. Okay. So this would be 80. Okay. So 80 here. So now 5 is left. So therefore 2, 2, 4, this is 4, and here this one is 1. Okay. So this one is also 0. So now this one is what? This one is equivalent to the plus 85. Okay. Now in order to represent the negative 85, what we have to do? We have to make this bit as 1. Okay. But all the other bits will remain same. So here it will be 1, 0, 1, 0, 1. Okay. That is the binary number, and it is now minus 85 in the 8-bit sign magnitude number. So that is the solution of part B of my question. Okay, this is the equivalent, or is 1 2 3 4 5 6 7 8 bit equivalent of this minus 85. So what is the step here? First of all, we have to find the magnitude of the positive number, and then we have to change the MSB of the binary number according to the sign of my decimal number. So that is the part B of my question. Similarly, in order to solve the part C here, that is how much? That is 100. So again I have to use the 6th bit here. So the 6th bit here will give me 64. So 64 and this is 32. So 64 and 32 is how much? That is 96. Okay, so how much is left now? Now we have 4 left. Okay, so we have to make this bit as 1 while the others will remain 0. Okay, so that is 0 1 2 3 4 5 6 and 7. Okay, so this is now what? This is for plus 100. Okay, so as the number here is already plus 100, so that is the binary equivalent of this plus, because now you can see that this bit is 0, so 0 means positive number. So that is for the plus 100. Okay, so now let me solve this minus 123. In order to represent the minus 123, what we have to do? Let me solve it here. So part D of my question, or let me go down. Minus 123. Okay, so in order to represent it with the binary numbers, so here I will have 0 1 2 3 4 5 6 7. Okay, these are all the powers of 2. So now in order to do it, 2 raised to power 7 is how much? That is 128. So that is higher than 123, so I am not going to use it. Similarly, now I have to use this one. This is 64 and then 32, that is 96 and 16. 96 plus 16 is how much? That is 11. So that would be 112. Okay, so how much is left now? 123 minus 112 is 110. So 11 is left. So therefore I will also include 8. So after including 8, 3 is left. So therefore I will make these two 1 1. So this is 2 raised to power 1 is 2, that is 2 raised to power 0 is 1. So this will be how much? That is my number, which is plus 123. Okay, so now in order to make it negative, what we have to do? We have to make this sign for this number, this also represent positive sign, while in order to make it minus 123, what I have to do? I just have to make this bit as 1 while the other will remain same. Okay, so that is okay 1 2 3 4 5. Okay, so this one and last two are these one. Okay, so that is now the binary equivalent of what? Minus 123. Okay, so that is for today, in which we have discussed the method of converting or expressing any signed decimal number with the help of a 8-bit sign magnitude number. So I hope it is now understandable, and I will see you with some more relevant examples in our upcoming videos. Thank you so much, and if you have any questions, please ask me in the comment box. Welcome back. So this is question number 24 of section 2.6, and we were talking about the sign numbers. Okay, so in today's lecture we will talk about the expression of each decimal number as an 8-bit in the ones complement form. Okay, so as I have previously told you that ones complement is one of the very feasible form for the negative decimal numbers. Okay, so the first term here we have is this minus 34. Okay, and we aim to represent it by using the ones complement. So first of all, what we have to do in first step we have to represent it in the binary form. Okay, so to represent it in the binary form, again using the same procedure, so 20 2 1, 2 2, 2 3, 4, 5, 6 and 7. Okay, so again I'm using the same sum of the product method of decimal to binary conversion, because I feel this is one of the very easiest one, and one can very easily remember this as well. Okay, so in first step of this procedure, what I have to do, I have to convert this minus 34 and take plus 34 of it and convert it into the binary one. Okay, so plus 34, so here I can see that this 2 raised to power 5 is the 32, which is the very nearest lower possible numbers of this 34, so writing it this one. Okay, so after it 32 and 34, there is only the difference of 2, so I can see that this 2 raised to power 1 is the 2. Okay, so these all are now zeros, making all these others are zeros, and I can see that this is what, this is the binary representation of this plus 34. Okay, so this is the binary representation of plus 34. In order to represent the minus 34 in the ones complement form, or taking the negative of it, what I have to do, I have to take the ones complement of it, and that would be the second step. So in second step, I have to take the ones complement of it. So taking the ones complement of all the binary digits here, what I will get here, I will get here 1 1 0 1 1 1 0 and 1. Okay, so that is the binary number which represents minus 34 in the form of its ones complement. Okay, so that is the answer of minus 34 or part A. Similarly, in order to represent this plus 57 in the binary number, so we can very easily see that this is a positive number, and it can be very easily represented by using the simple decimal to binary conversion, and there is no need to represent it in the ones complement form. So therefore we will just write it in the binary form. Okay, so plus 57, writing it in the binary form will give me how much? So using the same formulation which we have used here, so this 32 is the nearest lower form, while this 2 raised to power 6 is 64, which is greater than 57. So I will take this 2 raised to power 5. Okay, after it this is what, this is 2 raised to power 4, 16, 16 plus 32 is 48, again writing it. Okay, so 48 plus 8 is how much? That is 56. Okay, and this one is 57, so writing these terms as zeros. Okay, so the binary representation of it is 0 0 1 1 1 0 0 1. Okay, so that is the binary representation of plus 57, and as this decimal number is in the positive signed form, so therefore I am not converting it to the ones complement. Okay, the third one here, part C, is minus 99. Okay, C is minus 99, and that is the decimal. So again using the same convention, in which in first step what I have to do, I have to take this plus 99 and convert it to the binary form. Okay, so converting it to the binary form, again going back here. Okay, so here this 2 raised to power 6 is how much? This is 64, so writing it here as well. Okay, because 64 is the nearest possible lower number than 99, while here this is 2 to the power 5 is 32. 32 plus 64 is how much? This is 96, so I am also writing it. Okay, so 96 and 3 is left, so this one is 98 and this is 99. All other terms will remain 0 here. Okay, so that is what, that is the binary equivalent of my number, which is 0 1 1 0 0 0 1. Okay, so that is the binary number. Now in the second step, what I have to do, I have to take the ones complement of it, and this ones complement will be 1 0 0 1 1 1 0 0. Okay, so that is the form which represent the negative of this plus 99, so it will be minus 99. Okay, so this is what, this is the minus 99, and also shows me that this is the value which corresponds with this minus 99 as well. Okay, so that is the ones complement of my number which I have represented here. So here the last one is this plus 115, and again we can see that this is a positive number, and to represent it, what we have to do, we have to write the binary equivalent of it. Okay, so while writing the binary equivalent of it, what we will do here, this is the 64 plus 32 is 96. Okay, 96 plus 16 is how much? 96 plus 16 is 112. Okay, so how much is left? 3 is left, so this is now 3. This is basically the binary representation, and there is no need to take the ones complement of it. So therefore this will be 0 1 1 1 0 1 1. That is the binary equivalent of this plus 15. So that is the end of my question, in which I have represented the negative numbers with the ones complement, and similarly the positive numbers are represented by the corresponding binary numbers. So thank you so much, and I will see you with some more questions in our upcoming video. Welcome back, guys. So this is question 25, and here I have to represent each of the decimal number as an 8-bit in the 2's complement form. So the steps will remain same as we have done with the ones complement, so that wherever I will have here the negative numbers, I will first take the positive number, convert it to the binary one, and will take the 2's complement of it, and that would be the corresponding negative number of that decimal number. So the first question, or the first thing here I have, is this 12. Okay, so we can very clearly see that this is a positive number, so just writing the binary equivalent of it will be the sufficient one. So again, taking these terms here, so 0 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and 2 7. Okay, so the binary equivalent of this 12 will be how much? So here I can see that 8 is the closest possible number which is less than this 12, while this is 2 to the power 4 is the 16, which is higher than this. Okay, so 8 plus 4 is 12, while taking the others as 0. Okay, so this is basically the binary number which corresponds with it, and there is no need to take the 2's complement because this is already positive number. So 1 1 0 0, this is the answer of it. Similarly, in part B of my question, this is minus 68. Okay, so here I have to represent it, and therefore I have to take 2 steps. So in first step, what I have to do, I have to take the binary equivalent of plus 68. So the binary equivalent of plus 68 would be taking it here. So this is now 2 to the power 6 is 64. This is here. So 64 and 68, the difference between them is 4. So therefore there, this is the 4, while taking others as zeros. Okay, so what is this? This is the binary equivalent of it. So 0 1 0 0 1 0 0. Okay, in second step I have to find the 2's complement of it. Okay, so in order to find the 2's complement of it, what I have to do, I have to take the 1's complement of it. So 1's complement of it will be 1 0 1 1. Okay, and 0 1 1. This is the 1's complement, and in order to take the 2's complement of it, I have to add 1 with it. So adding 1 with it, what I will get, 1 1 is 0, 1 will be carried here, this is 0, this 1 here, so 1 1 1 1 0 1. Okay, so what is this? This is the 2's complement, which is the alternative of this minus 68 in the binary number. So that is the binary equivalent of minus 68 in the 2's complement form. Okay, so that is the number. Similarly, the third one here is 101. Again, this is a positive number, and just taking the binary equivalent of it will be the sufficient one here. Okay, so I'm not going to convert it here, but you can try it over it, that just writing the binary equivalent of it will be the sufficient one. While the last one here is minus 125. Okay, so D is minus 125. Okay, so that is again a negative number. So again I will follow two steps. So again, first step, binary equivalent of plus 125, how much would it be? Let me write it here, converting it by using it. So what I will get here, it will be, this is 64, 32, 96. 96 plus 16 is 112, 112, 8 is 120, this is 124. Okay, so 124 and 1 is 125. So that is what, that is the binary equivalent of plus 125. So here it will be 0, 1, 1, 1, 1, 1 and 0, 1, 1, 2, 3, 4, 5, 6. Okay, so that is the binary equivalent of 125, and in the second step I have to find the 2's complement. So in order to find the 2's complement of it, first of all I have to take the 1's complement. So 1, 0, 0, 0, 0, 0 and 1, 0. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the 1's complement, and adding with it 1. Okay, so it will be 1, 1, 0, 0, 0, 0, 0, 1. Okay, so what is this? This is the 2's complement, which is the binary equivalent of minus 125. Okay, so in this manner we have covered that how to calculate the 2's complement of the negative numbers, while the positive numbers binary equivalent will remain same. So that's the end of today's lecture, in which we have solved question 25, and I will see you with some more interesting questions in our upcoming video. See you soon. Welcome back, guys. So this is question number 26, in which we are given different binary numbers, and these are the signed binary numbers, and we have to determine the decimal equivalent of these numbers. Okay, so as previously discussed, these are basically the 8-bit numbers. Okay, so let me have these 8-bit numbers. Okay, so these are all the 8-bit numbers, while here this 8-bit is the signed bit. Okay, so whatever here will be, if this will be 0, so what is meant by 0? This is a positive number, while if it is 1, this it means that that is a negative number. So here now let us first use these bits here and see that what are those numbers by converting it to the decimal equivalent. So the first number here is, this is part A, and that is 1 0 0 1 1. Okay, 0 0 and 1. So these are basically the 2 raised power 0, 2 1, 2 2, 2 raised power 3, 2 raised power 4, 2 raised power 5 and 2 raised power 6, while this is a sign bit. So this sign basically represents that this is a negative number. Okay, so this is for the sign, while others will be used for the decimal conversion. So here that's why it will be 1 multiplied by 2 raised power 0. Similarly, it will be 0. Here it will be 0 as well, while this one will be multiplied with 2 raised power 3. Okay, this one will be multiplied with 2 raised power 4. Okay, now these zeros are also multiplied with these terms, but the resultant of this multiplication will be 0. That's why I have written them here like this. Okay, similarly 0 multiplied with 2 raised power 5 is 0, and this one will also give me 0. Okay, now adding them, what will I get? This is 1 plus 0 plus 0 plus 8 plus 16 plus 0 plus 0. Okay, so how much would it be? That is 16 plus 8 is 24 plus 1 is 25 with this one. So this is now how much? That is 25, while this one is 1. So therefore this equivalent will be minus 25 in decimal numbers. Okay, so the equivalent of it is minus 25. Similarly, now converting it into the decimal as well. So now we can see that this bit here is 0. Okay, so that's why it would be a positive number. Similarly, 0, 1, 2, 3, 4, 5, 6. Okay, this 6 is how much? This is 64 plus 32, 96. 96 plus 12 is 96 plus 12 is how much? 96 plus 12 is 8. That is 108. Okay, 108 plus 4 is how much? That is 112. So this is now plus 112, or the decimal equivalent of 0 1 1 1 0 1 0 0. So that is in decimal, so that is in binary. So now the decimal equivalent of it is this plus 112 in this one. Okay, now solving the last of it, which is now C of it is 1 0 and all others are 1. Okay, so how much would it be? So we can very easily see that this is now 1, so it basically shows me the negative number. Okay, now as this one is the negative one, so all the others except this one are here 1 1. So here it will be 1 1 1 1 1 1. So how much would it be? So that is 2 raised power 5. So that is how much? That is, so here I will have multiplying all these terms. What I will get here? I will get 1 plus 2 plus 4 plus 8. Okay, plus 16 plus 32. Okay, and that would be in 9s. So 32 plus 16 plus 8 plus 4 plus 2 plus 1. So this is 3 plus 4 is 7. 7 8 is how much? 7 8 is 15. 15 plus 16 is 31, and this is minus 63. So the decimal equivalent of this number is how much? That is minus 63 in decimal. So that is the procedure in which the sole method or the crucial task is to find that whether the number is negative or positive, and all of that basically depends upon these two MSBs, the most significant bits, either that can be 0 or 1 as well. So that's it for today, in which we have discussed the signed number conversion from binary to the decimal number. So thank you so much. This is question number 27. And here we are asked to determine the decimal value of each signed binary numbers in the ones complement form. Okay, so all the numbers here which are mentioned, so these are basically the ones complement representation of any decimal number. So in previous lectures we have determined the binary equivalent of the positive and negative numbers. So today we are going to discuss the binary to decimal number conversion. Okay, so basically there are two methods. The first method here is, let me take the first part of it here. So 1 0 0 1 1 0 0 1. Okay, so that is basically the 8-bit binary number. Okay, so what we have to do here are basically two methods. Let me first discuss the first method. Okay, so according to this method, what we have to do, let me write it by using this green color. So what we have to do, this is the ones complement. So the number we have here is 1 0 0 1 1 0 1. Okay, so as the leftmost bit here is 1, so we can see that this is a negative number in the decimal equivalent. Okay, so what we have to do, first of all, we have to take the ones complement of it. Okay, so ones complement of it will be 0 1 1 0 0 double 1 and 0. Okay, so that is the ones complement of it, and then we have to convert it to the binary one. So again the binary equivalent of it will be how much? So again writing 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and 2 7. Now writing these numbers here, what we will get, this is 0 1 1 double 0 double 1 and 0. Okay, so multiplying each term with the corresponding bit here, what I will get here, I will get here 2 1 is 2, this is 2. Okay, this 1 multiplied by 4 is 4, this will be 0, this will be 0. This is how much? 2 raised to power 5 is 32. Okay, and this is what? This is 64. So now getting it, what I will get, 64 plus 32 is how much? 96. 96 plus 4 is 100, and then 102. So that is 102, and previously we have seen that it would be a negative number due to this bit, so therefore it will be minus 102. So this is the method number 1, in which we have seen that the answer is minus 102. Similarly, in order to find the decimal equivalent of it by using the second method, so second method here will be the second method will be, so let me first write here 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and minus 2 7. We have to write the negative sign with this 2 raised to power 7, and now we have to write the bits here. So let me use the blue color for the method number 2. So now writing the bits here, so I will get here 1 0 0 double 1, okay, double 0 and 1. Now converting it, what I will get, again the same procedure. So here I will get 1, okay, plus this is 8, this is 8, this is 16, okay, and this is how much? This is 128, so negative of it is minus 128. Okay, so now I will have 128 plus 16 plus 8 is how much? That is 24, plus 1 is 25. So here I have 25. So here minus 128 plus 125 is how much? That is minus 103. Okay, so at the end we will get, when 103 we have to add 1 with it, so I will get here minus 102. Okay, so this is from the method number 2, while this minus 102 is from method number 1. So we can see that both the answers are correct. So you can see that whatever method you want to use, it will be up to your convenience, so whichever method you like to do here. Okay, so that is the first video in which we have discussed the two methods which you can use. So this is method number 2, which I have represented with this blue color, and this is method number 1, which is done by this green color. Okay, so I will see you with these two parts in our upcoming video. Till then, take care of yourself. Welcome back, guys. So this is question 27, and this is part B of 8, in which we have seen that there are basically two methods to convert any signed ones complement form to the decimal one. Okay, so previously we have talked about the part A of it. So now let us start part B of it. So for it, let me first remove it. Okay, as I have told you that whatever method you found convenient, you can do it. So let me use method number 2 for solving the part B of my question. So here again, in order to solve it by using the method number 2, so what I will get, there will be 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and minus 2 7. Okay, now writing the bits here, what I will get, I will get here 0 1 1 1, okay, 0 1 and double 0. Okay, now converting it and multiplying each bit with the corresponding value here, what I will get here 0 0, here what I will get here, it will be 4, okay, plus here this will be 8 is multiplied by 0, this is 16, okay, plus 32, and this is 64. Okay, so converting them to the decimal equivalent, what I will get, 64 plus 32 is 96, 96 plus 4 is 100, and this is 116. So this is 116. This bit is already nullified by multiplying this term with the 0, and we have got this 116, which is already a positive number. So therefore the answer will remain same, which is 116. Okay, similarly, in order to solve it by using the method number 1, and this was a method number 2. So in order to solve this question by using the method number 1, we can see that here the number is 0 1 1, okay, 0 1 0 0, and here we can see that this bit is already 0. So therefore we will see that we can conclude from it that the answer of it will be positive. So therefore we are not going to take the ones complement of it, and the number here will remain the same here. So therefore converting this one, okay, when I will convert it to the decimal one, what will happen? It will be the same procedure which we have followed here. So therefore the answer of it will also remain 116 in the decimal form. Okay, so we have seen that the answer from both methods will remain same here. Okay, similarly, talking about the last part of our question, so let me talk about the last part of our question. So the last part of our question is this one. Okay, and let us solve it by using the method number 2 again. So method 2, following the method 2 here. So the question here is 1 0 and all the ones here. So therefore what I am going to do here, I am going to follow the method number 1. So here by following the method number 1, what will happen? It will be a lengthier method. Why? Because all the bits here are basically 1 here. Okay, so you have to use your own common sense that which method you should have to follow. So therefore when I will follow method number 2, this will be a lengthier one, and you have to make many calculations, because you can see that this is 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and minus 2 7. Okay, so writing bits here, what I will get 1 0 and all others will be 1. Okay, so it will be a quite lengthier method, because each bit and each number here will be added together, but not this one. All the others will be added together, and this will be a lengthier process. Despite it, the method number 2, using the method number 2 here, what we have to do here, we have the number which is 1 0 1 1 1 1 and 1 1. Okay, so 1 2 3 4 5 6 7 8. So here we can see that this bit is 1, so therefore the answer will be a negative number. Therefore what we have to do, I am going to revert all the bits here. So here the ones complement of it will be 0 1, and all the other terms will be 0. So 1 2 3 4 5 6 7, and this one is 8. So all the bits are inverted. So now converting it to the decimal form, what I will get, 2 0 2 1 2 3 2 4 2 5 2 6 and 2 7. Okay, writing these bits here, what I will get, 0 1 0 0 0 0 0. Okay, so I will get here only this term will be multiplied with it, and I will get 2 raised power 6, which is 64. Okay, so as I have previously told you that the answer here will be negative, so therefore the answer here is minus 64. So from this method we have calculated all the terms very easily. Unless and until we had to find all the terms here, what we had to do, we have to add this one with this one with this one. Okay, all the terms here will be added together, and what we will get here, 3 plus 4 is 7, 7 plus 8 is 15, okay, 15 plus 16 plus 32, and here it will be how much? That would be minus 128, okay. So 32 plus 16, this is how much? 48. So 48 plus 15 is how much? This will be 63. So minus 128 plus 63, okay, sorry, this is 63. So how much would I get? I will get here minus 65, okay. So as this is a negative number, I have to add 1 with it. So here I will get minus 64. So you have seen that this one, method number 1 here, let me use the red color here. So method number 2 here is lengthier than the method number 2, okay. So you have to look at your own convenience and follow the method which you find feasible for you to use in any condition, okay. So that is the end of our question number 27, in which we have gone through different scenarios that whichever method we will use and will be better one. Sorry, this is the method number 1 and this is the method number 2, okay. So that's it for today, and I will see you with some more interesting questions in our upcoming video. See you soon. Welcome back, guys. Question number 28, and here we have to determine the decimal value of each signed binary number in the 2's complement form, okay. So here the method will remain the same. The only method we will follow here will be that in which I have to write the powers of 2's, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6 and minus 2 7, okay. So the method here will remain the same as we have to follow for finding the decimal equivalent from the 1's complement forms in our previous videos. But what will be the difference between the 2's complement and 1's complement decimal values? There whenever we got any negative numbers, we had to add 1 with it at the end, but here we are not going to do so. So therefore the first question here is 1 0 0 1 1 0 0 1, okay. So let me write here. So 1 0 0 1, okay, 0 0 1, okay. So these will be multiplied together, and here I will get what I will get here. I will get here 1 plus this is 8, okay, this is how much? This is 16, okay, and this is minus 128. So now minus 128 plus 16 plus 8 is how much? That is 24, plus 1 is 25, okay. So at the end I will get minus 103, okay. So that is the decimal equivalent of this number, and the answer of it is minus 103 in the decimal form, okay. Similarly, for the next question we have, let me remove it, and just by writing their values here, what I will get? 0 1 1. So here 0 1 1 0 1 0 0, okay. So what I will get here? This will be 4 plus this is 16 plus here 32 plus 64, okay. So adding them together, what I will get? 64 plus 32 is 96, plus 4 is 100, and 16 is 116 in decimal. So the answer of it is 116 in the decimal form, okay. So that is the decimal equivalent of 116. Now similarly, finding the decimal equivalent of this number, what we have to do, again let me remove it, and writing all the values here, 1 0, all the ones, okay. And now finding them, what I will get here? This is 1 plus 2 plus 4 plus 8 plus 16 plus 32, okay, and this is minus 128, okay. So let me solve them. Minus 128 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, this is 63, okay. 63 minus 128 is minus 65. Okay, so that is the decimal equivalent of it, and we will see that it is now this one. Okay, so that is the sole difference between the 1's complement and 2's complement, what we have seen in our previous videos. And by following the same procedure, which was basically the 1's complement form in our previous video, so what if you use the conventional method, what you have to do? Okay, so in that video, let me use the same procedure here for this number. So if I have 1 0 1 1 1 1 1 1, okay, so this is basically a number, and here this 1 means this will be a negative number. Okay, so if it will be a negative number, let me first invert all these numbers. So what I will get, 0 1, and all the others will be zeros. Okay, so once I will get it, let me add 1 with it, and I will get here what, this will be 1 0. Okay, as this is a 2 form, that is 0 0 0 0 1 0. Okay, so I will get this number. Now writing the binary equivalent of it, what I will get, this is the only bit here and this one here, so this will be 1 plus this is what, this is a 6 bit, so 2 raised to the power 6 is 64. So 64 plus 1 is how much? That is 65, and as I have told you that it will be negative number 1, so it is now minus 65 in decimal, which is the same as this one here. Okay, so the same procedure will lie also here, but what you had to do after inverting all the bits, what you had to do, you had to add 1 with it. Same will lie for this one as well. Just take a look at it and give it a try, and you will get the same answer as we have done here. Okay, so that's it for today, in which we have discussed the two methods for finding the decimal value from the 2's complement form. Okay, so that's it for today, and I will see you with some more questions in our upcoming video. See you soon. Welcome back, guys. So in the previous video we have solved the part A and part B of this question 31. So today we will try to solve part C and D. So in part C of our question, we have minus 46 and 25, and I have to add them together. So here it will be minus 46 and add it with the 25. Okay, so how much would it be? I can see that here the operation is the subtraction, so therefore 6 and 5 is this 1, and 4 2 is 21, and the sign with this higher number is negative, so therefore it will be minus 21. So let us see that whether we can do it with this by using the binary operations or not. So here again, let me convert them to the binary. So first I have to convert this 25 to the binary, then finding the 2's complement of this minus 46. So 25 in binary will be, so I can see that this is the 1. Okay, so this because 2 raised to the power 4 is 16, and that is the value here, which is lower than this 25. Okay, this is now 16. 16 plus 8 is 24. Okay, and this last one is 25. All the other terms will remain 0. Okay, so that is what, that is the binary equivalent of 25. While what will be the binary equivalent of 46? So the binary equivalent of 46, let me find it here. Okay, so the binary equivalent of it will be 2 0 1 2 3 4 5 6 and 7. Okay, so the number here which is less than this 46 is 32. So this is 32. Okay, 32 plus 16 is 48, which is higher than 46. So therefore I have to take this 8, which is now 32 plus 8 is 40. So this is now 44, and then 2 46. All the other terms will be 0 here. Okay, now taking the 1's complement of it, what I will get here, 1 1 0 1 0 0 0 and 1. Okay, this is the 1's complement, and to find the 2's complement of it, what I have to do, I have to add 1 with it. So I will get here 0 and 1. So this is 1 0 0 1 0 1 1. Okay, so that is what, that is the 2's complement equivalent of minus 46. Okay, so now writing this value here, what I will get, 1 1 0 0 1 double 0 1 0. Now adding them together, I will get 1 1 0 1 0. Okay, 1 1 1. So we can see that this is the 2's complement of this minus 21. Okay, so how can I say that this is the 2's complement, because this one doesn't correspond to the 21, because 21 is the lower number. So therefore what I have to do, I have to find 2's complement. So now finding the 1's complement of it, what I will get, 0 0 0 1 0 1 0 0. Okay, so now adding with it 1. Okay, what I will get here, this will be 1 0 1 0 1 0 0 0. Okay, so I will see that this will be how much, this will be the plus 21. Okay, because this one is the 2's complement of anything which I will get here. So this will be 2 raised to the power 16 plus this is now how much, 4 plus this is 1. Okay, so I can see that this is the answer which I have found out, and that is basically in the form of the 2's complement. Okay, so that is the answer here, which also corresponds with this minus 21 as well. So but that is basically the 2's complement of plus 21, which basically shows us that this is a minus 21. Okay, so that is the answer of my question, in which I have added the values of minus 46 and 25. So welcome back guys. The last question here is that where both the numbers are negative. So what I have to do, I have to add 110 with minus 84, and from it I will get minus 194. Okay, and that is the decimal. So how to do it in the binary form? So what I have to do, first of all, I have to take 110, okay, and convert it to the binary. Similarly, the binary equivalent of 84, and first of all I will convert them both to the binaries. Okay, and then find their 2's complement, and then I will add them together. Okay, their addition will give me the answer. So the binary equivalent of 110 is how much? So let me find out here. 2 raised to the power 5 is 32, this is 64. So let me write here, this 164 plus 32 is how much? This is 96, and 96 plus 16 is 112. Okay, so I have to find this 8. So this will be 96 plus 8 is how much? So 96 plus 8 is 104. 104 plus 4 is 108, and 108 plus 2 is 110. All the other terms will be 0 here, and that is the binary equivalent of plus 110. So in order to find the 2's complement of it, what I have to do, I have to 1's complement of it. So 1's complement of it will be 1 0 0 1 0 0 0 1. Okay, and the 2's complement of it will be found out by adding 1 with it. So adding 1 with it, I will get 0 1. Okay, so 1 0 0 1 0 0 1. Okay, so that is what, that is the 2's complement of 1 1 0. So that is equal to how much? That is the binary equivalent of this minus 110. Okay, so let me write it here first. 1 0 0 1 0 0 and 1 0. So that is what, that is minus 110. 10. Now in order to find the binary equivalent and 2's complement of minus 84, first of all let me find the binary equivalent of plus 84. So for that let me use here this 2 raised power 6, which is how much? That is 64. Okay, so 64 plus 32 is 96, which is higher than 84. So therefore 64 plus 16 is how much? That is 80. Okay, and 80 plus 4 is 84. All the other terms will be 0 here. Okay, so now in order to find the 2's complement, first of all find the 1's complement of it. Okay, and then for this is the 1's complement, and for the 2's complement let me add 1 with it. So I will get here 0 0 1, so 1 1 0 1 0 1. Okay, so that is the 2's complement, which corresponds to this minus 84. So now writing it here, now I will get 1 0 1 0. Okay, double 1 and double 0. Now adding them together, what I will get here, adding them together I will get 0 1 1 1 1 1. Okay, there I will get 0 and 1 1 is how much? That is now 0 and 1. So I am getting 1 here. So what does it mean? It shows me that the overflow has been occurred. So why is there an overflow? Because 194 is the 8-bit number. Okay, you can see that here out of the 7 bits, how many numbers can I get? I will get 0 to 127, but this is not in this range, so therefore overflow has been occurred. So therefore I will discard it and I will see that what can be found out here. So therefore using this here as well, I will see that this is basically the negative number, which is represented with these 9 bits. Okay, so that is the overflow condition, and we will talk about it in our upcoming video. So till now you have seen that how to add both the negative numbers, one positive, one negative numbers, and different cases were presented to you, in which I have told you that in order to add 2 numbers or more than 2 numbers, what you have to do, you have to represent the negative decimal numbers with its 2's complement binary equivalent. Okay, so that's it for today, and I will talk to you about the overflow condition in our upcoming video. Till then, take care of yourself and I will see you soon. So welcome back guys. This is section 2.8, which is related to the hexadecimal numbers. So what are basically the hexadecimal numbers? What are their benefits and where can we use them? Okay, so previously we have seen that the binary numbers which we have 1 0 1 0, let's say this is basically a binary number. So this is basically the 4-bit binary number. Okay, and it is very easy to represent it by using these 4 bits. But if we have more bits like this one, like we can see that in computer systems we usually have the integers, 8-bit integers. Okay, similarly int 16, int 32, okay, int 64 as well. Okay, so what is this? In int 8 we have 8-bit integer, we have 16-bit integer in int 16. Okay, similarly in int 32 we have 32 bits, and in int 64 we have 64 bits integer. Okay, so it is very difficult for us to represent all those by using the bits. Okay, so suppose if we have a bit like here 1 0 1 1 0 1 1 1 0 0 1 1 1. Okay, this is basically these are basically the bits. So we don't know that how many number of bits are here, but it is very difficult for us to represent them in the binary form if we have more than 4 bits or 8 bits. So if we have 16 bits, so it is also very difficult for us to represent them by using these ones and zeros. So therefore another system has been introduced. What it does is that it takes 4 bits, okay, and convert it to a single hex code. That is basically called the hexadecimal number. Okay, so that is basically the underlying concept, that why does hexadecimal numbers are used, because in hexadecimal numbers each bit here we have is basically consist of 4 bits. Okay, so in computer system you would usually have seen that many codes are written like 0x54 ACD 05, like this one. Okay, so what does this X means? This X basically represents the hexadecimal number, and this is basically the hexadecimal code. Okay, so this is basically the code which is the hexadecimal equivalent of any number which computer has to show us. Okay, so that is the underlying concept, that why hexadecimal numbers are used in the computer systems and computer engineering. Okay, so we will start to solve the questions in our upcoming video. So today we have discussed that what are the benefits of using the hexadecimal numbers. Thank you so much, and I will see you soon. So in previous video we have seen the benefits of using the hexadecimal numbers and why we use the hexadecimal numbers in our computer system and binary number system. Okay, so today we are given a question in which we have to convert each hexadecimal number to binary. Okay, so before it we have to see that how a binary number can be converted to the hexadecimal, or hexadecimal number can be converted to the binary number. Okay, so as the name says that it is basically the hexadecimal number. So hexadecimal means 16. Okay, so therefore hexadecimal number system basically consists of 16 numbers which ranges from 0 to 15. Okay, in decimal, while this 15 in hexadecimal is called F. Okay, so this is basically the range of a hexadecimal number. Okay, so this is basically the concept behind the hexadecimal number, and in order to convert any number to the hexadecimal number we have a table which can be written here like so. That is basically the table in which we have different numbers. So this is first of all 0 in decimal. In binary, as we have 16 numbers, so to represent 16 numbers we should have at least 4 bits. Okay, so therefore the binary number we will see here will be consist of 4 bits. Okay, and in hexadecimal it is 0. Okay, so 0 0 0 0 and all these up to 9, these will be similar as that of the decimal, but after 9 the decimal numbers will be the combination of the numbers from 0 to 9, while here we will have A, then B, C, D, E and F. Okay, so therefore I have told you that these starts from 0 and ends at what? Ends at F. Okay, so in order to convert any hexadecimal number to the decimal number, what we have to do? So suppose we have here 46 in the hexadecimal number. So what we have to do? First of all, we have to see the hexadecimal equivalent of 6. Okay, which is at the right side of my number. So the hexadecimal equivalent of number, my number is what? That is 6. So 6 is 0110. Okay, so let me write 0110. Okay, this is the binary equivalent of this hexadecimal number. Similarly, in order to convert this 4, what we have to see? We have to see the binary equivalent of this hexadecimal number again. So what is this? Let me see here. So this is now here, this is 0100. So let me write here 0100. Okay, so now refining it, it will be 0100 0110, and this is the binary equivalent of my number, that is in hexadecimal 46 16. Okay, so that is, sorry, this is was basically 16. So this is the conversion of my number to the hexadecimal number. Similarly, in order to convert the part B, which is 54 16, okay, first we have to see that what is this 4 equal to. That is again 0 1 0 0, okay, and 5 equal to 0 1 0 1. So 0 1 0 and 1. So that is the binary equivalent of 54 in hexadecimal. Okay, so now let me remove them and start solving other questions. So part C here is B4 16, okay. Similarly, following the same procedure, the 4 here will be how much? That is again 0 1 0 0, okay, 0 1 0 0, and B is how much? That is B, which is 1 0 1 1, okay. So 1 0 1 1. So that is the binary equivalent of the number which is here, okay. Part D here is 1A3 in 16, okay. So now we can see that we have 3 digits. So first of all, writing the equivalent of 3, that is here. So that is 0 0 1 1 0 0 1 1, okay. The equivalent of A is how much? That is 1 0 1 0. So 1 0 1 0, okay, and the last one here is 1, which is here. So 0 0 0 1, okay. So 0 0 0 and 1, while this one is this one, okay. So we can see that here we have converted them in the parts of 4s and 4 parts, which are basically 1 0 1 0. This one is here as well, okay. So each bit here is, this is 1, this is 8, this is 3. So that is the hexadecimal equivalent of the number. Similarly, we have here, let me remove it again, okay. This is part E, and it is here FA16, okay. So A is here, we can see that A is 1 0 1 0 1 0 1 0, okay, and F is here. This is 4 times 1, so 1 1 1 1, okay. So this is here, okay. So we can see that this one is here while this one is here. So that is the binary equivalent of my number. Similarly, part F of my question, A B C in 16, again at 3 digits we have here in the hexadecimal number. Now writing the equivalent of C here. The equivalent of C is here 1 1 0 0. Let me use this green color. So 1 1 0 0 for this C, okay. For B it is 1 0 1 1. Here we can see that 1 0 1 1. So for B 1 0 1 1, okay. And for A we can see that for A it is 1 0 1 0, okay. So taking it and writing it here, so 1 0 1 0, okay. So we can see that this is a number, this is another 4-bit number, and the last one is here, this one. So that is basically the binary equivalent of my number, okay. So we can very easily see that here the 12 bits are very easily shown by using the 3 hex codes, okay. So that is the efficiency of my hexadecimal number. So the last one here is, what is the last one? In the last one we have 4 digits which are A B C D, okay. So we have here A B C D 16, okay. So therefore now using the same procedure in which the D, first of all we have to write the codes of D, then C, then B, and at the end we have to write A. Okay, so let me write them here. So initially the code for D is how much? That is here 1101. So 1101 here. Okay, so that is for D. For C we have here 1100. So here we have 1100. Okay, so this is for this one. These 4 bits are for this, while these 4 bits are for D. Okay, for B we have here, we can see that this is for B, so 1011. So 1011, this is for this B, and for A we have this 1010. Okay, so this is for this number. So we can see that here we have these 16 bits which are very easily represented by these 4 codes which are in hexadecimal numbers. Okay, so that is for today, in which we have discussed the hexadecimal numbers and how does a certain hexadecimal number can be converted to its binary equivalent. From the next video we will try to solve some more questions which will be related to the hexadecimal numbers. So till then, take care of yourself and I will see you soon. Welcome back, guys. So this is question number 38 of section 2.8, in which we have to convert each binary number to the hexadecimal number. Okay, so in previous question we have seen that how to convert a hexadecimal number to its binary equivalent. So today we will see that how to convert a binary number to the hexadecimal number. Okay, so we are again going to use the same table which we have previously used. Okay, so here all the binary codes are written, their decimal equivalent is also written here in the leftmost column. Okay, and the equivalent hexadecimal numbers are also mentioned here in the rightmost column. So let me start it from part A. So here we have these all ones, so this is basically a 4-bit number. So from this table we can see that in binary this all ones is equal to F, so therefore the hex equivalent of it is F, and that is in 6, while this was a binary number. Okay, so that is the answer of part 1. For part B we have 1011. Okay, so in this table we can see that 1011 is how much? That is B, so B is B16. Okay, so that is the answer of part B. For part C we can see that here we have 1 1 1 2 3 4 5 ones. Okay, so 1 2 3 4 5, we have 5 bits here. So what we have to do in this situation, what we have to do, we have to combine the 4 bits in each of the number, and we will start from the LSB. Here we can see that it is the LSB, while the leftmost bit will be the MSB, which stands for the most significant bit. Okay, so we can see that here we have these 4 bits and these are now mentioned here. So 1 1 1 1, this is the F. But what about this one? This is 1, so we don't have anything here, so therefore we ourselves should have to put zeros here. So after putting it, we will see that it will become a 4-bit number. So now this 4-bit number will give me a number which is 0001, so that is equal to 1 here. Okay, so that would be the 1F in the hexadecimal number. So that is the answer of part C. So in part D we can see that here we have how many bits? So here these 4, okay, and the last 4, because this is an 8-bit number, so we can see that 1010 is how much? That is 1010, so that is A. Okay, similarly this is also 1010, so this is also A, so that is AA16. That's it, that is the hexadecimal equivalent of part D. Similarly in part E of my question we will start to do it from here again. So that is a 4-bit number. Again this is a 4-bit number because in total this is the multiple of 4, because in total number of bits here are 8. So therefore 1100 is here equivalent to C. Okay, so we can see that 1100 is C. Okay, and 1010 is how much? That is A. So that is the hexadecimal equivalent of AC, and this is the answer, while this one is here. The last one here is this one, so let me start here. So this is now this one, and the last one here is here. So now 1011 is how much? So 1011, this one, okay. 1011 is B, this is B, and 1011 again B, okay. So that is the hexadecimal equivalent of it, okay. So that's it for today, in which we have seen that how easy it is to convert any binary number to the hexadecimal number if we have this table, okay. So here in this table we have seen the benefits of converting any binary number to the hexadecimal, similarly any decimal number to the hexadecimal number as well, okay. So that's it for today, in which we have seen the benefits of it, and in our upcoming video we will see some more questions. Till then, take care of yourself. So welcome back, guys. Today we are going to talk about the hexadecimal to decimal conversion, okay. So here we have different parts of this question in which we are asked to convert each hexadecimal number to the decimal number, okay. So the first one here is 42 in hexadecimal, okay. So what we have to do, our approach will be to first convert it to the binary, okay, and from binary we will convert it to the decimal equivalent, okay. So here will be our approach. So as we have again this table, so why would we use this table? Because of converting this hexadecimal to the binary one, okay. So what we have to do, we have to write the binary equivalent of 42. So let me write it here. This is 42, okay. So the binary equivalent of 42 will be, as this is the hexadecimal number, so writing the equivalent of 2 here, what it would be, we can see that the equivalent of 2 is, this is the hexadecimal number and its equivalent, binary equivalent, it is here. So it will be 0010, okay. So that is the binary equivalent of it. Similarly, the binary equivalent of 4 will be how much? We can see that this is 4 and its equivalent is here. So 0100, okay. So writing here 0100, so that is the binary equivalent of this 42, okay. What we have to do now, we have to convert it to the decimal, okay. So converting it to the decimal, what we have to do, we have to use the same procedure which we had previously used. So here it will be 20, 21, 22, okay, 23, 24, 25, 26 and 27, okay. So we can see that only 2 raised power 6 multiplied by 1 plus 2 raised power 1, these two are ones here while others are zeros. So 2 raised power 6 is how much? That is 64, okay, and this is how much? This is 2, okay. So the decimal equivalent of it is 66 with the base 10, okay. So the decimal equivalent of 42 is 66 with the base of 10, okay. So that is the procedure we can follow for all the other terms as well. So let me start part B here. So to start part B here, what we have to do, let me clear it, okay, and here this one as well, okay. So now this 64 in hex, what we have to do, first we have to find the binary equivalent of it. So binary equivalent of 4 is this one, this is 0100, so 0100, okay, and the binary equivalent of 6 is how much? That is here, this is the hex, and 0110, so 0110, okay. So that is the binary equivalent of 64, okay. We can write here, this is the binary, okay. And in order to write the decimal equivalent of it, what we have to do, again we have to write here 20, 21, 22, 23, 24, 25, 26, 27, okay. Converting it to the decimal, what we will get here, only this 2 raised power 2, this is 1, while this one 2 raised power 5 is 1, and this 2 raised power 6 is 1. All the other terms are 0 here. So now writing them here, 4 plus 2 raised to power 5 is 32, okay, and this 2 raised to power 6 is 64. So 64 plus 32, that is 96. 96 plus 4 is 100, okay, and this 100 is in decimal, so that is the decimal equivalent of my number, which is now here, okay. So that is the procedure of finding the equivalent decimal number of any hexadecimal number, okay. Similarly, now removing it, and for part C of my question, what we have to do, that is 2b16, okay. Again, the binary equivalent of these will be, the first one here is b, so b is, we can see that this is b, so that is 1011, 1011, and the binary equivalent of 2, we can see that this is 0010, okay. So that is the binary equivalent of it. Now converting it to the decimal, so that is 2021, 22, 23, 24, 25, 26, 27, okay. So that is what, that is the binary, okay. So now here we can see that only 2 raised to power 0 plus 2 raised to power 1, 2 raised to power 3, and 2 raised to power 5, these terms are multiplied with this 1 and will give me the values whatever weight these would have, okay. So we can see that these are the values. So now it would be 1 plus 2 plus 8 plus 32, okay. So now writing them, what I will get, 32 plus 8 is 40, 40 plus 3 is 43, okay. So that is what, that is the decimal equivalent of my number. So we can see that the decimal equivalent of 2b is 43d. All the other terms will also remain same, and the procedure of finding their equivalent will be just like here we have done here, okay. So this is the solution of part C. Similar will happen with this 4d, in which first we have to write the binary equivalent of 4 and then d, and then converting it to the decimal will give us the decimal equivalent of it, okay. Similarly here, this ff, we can see that we can see that every f is composed of the 4 bits, 1 bits in its binary equivalent. So therefore this ff will contain 8 ones, okay. So okay, we have to convert them, and we will see that we will get some numbers in the decimal, okay. So it will be easier to convert them into the decimal equivalent. Similarly, we will do it for this one as well, where b and c are 2 numbers. So c is equivalent to what, that is 1100, okay, and b is equivalent to what, that is 1011, okay. Then we will convert it to the decimal from this binary number, and we will see that the equivalent will be the decimal equivalent of this number, okay. So the last two are basically composed of these 3 hexadecimal codes, okay, and it would be somehow different to calculate their results. So we will do it in our upcoming video. Till then, practice all the stuff which we have covered today, and I will see you with some more stuff in our upcoming video. Thank you so much, and I will see you soon. Welcome back, guys. So previously we have seen the conversion of the 2-digit hexadecimal number to the decimal one, and we were left with these g and h parts, okay. So let us first find the decimal equivalent of this g part. So g is 6, f and 1, okay. So as this is a hexadecimal number, what we have to do, we have to find the binary equivalent of these. So 1 is, we can see that this is here, okay. So it would be 0001, okay. F is how much, that is 4 times 1, okay. So 1 1 1, and this is 6. We can see that this is the binary equivalent of f, while 6 is how much, that is 0110, okay. So 0110, okay. So these are here. Now as we have found them out, what we have to do, what is the next step here, we have to find the decimal equivalent of this binary number. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so from here we can see that all the numbers which are multiplied with these ones here, so here the weights which has a multiplicative factor of 1 will be 20. Okay, similarly adding them, this 2 raised to the power 4, okay, this 2 raised to the power 5, this one 2 raised to the power 6, okay, 2 raised to the power 7. Okay, so we can see that it is this one, this one is also this one, this one, this one. Well, now here 2 raised to the power 9 and 2 raised to the power 10, so 2 raised to the power 9 plus 2 raised to the power 10. Okay, so now adding them, we will get our number. So in order to add them, what we have to do, this is 1, this is 16, okay, this is 32, this is 64, this is 128. Okay, how much is this? This is 512. Okay, and this is 1024. So in order to add them, you may use a calculator. So let us use a calculator here. So here, in order to add them, what we will do, 1 plus 16 plus 32 plus 64 plus 128 plus 512 plus 1024. Okay, so what we will get here, 1777. So 1777, that is the decimal equivalent of my number here. So what was that? This was basically the binary number. Okay, this was a hexadecimal, and now at the end we have got the decimal equivalent of my number. Okay, so that is about part G of my question. Similarly, we can also do it for part H as well. So let me do it for part H. Okay, so part H is A, B, C. Okay, the equivalent of C is here. We can see that that is 0000. Okay, the equivalent of B is 1011, 1011, and the equivalent of A is here, that is 1010, 1010. And now multiplying them with the weights it has, so we can see here that this is the hexadecimal, this is the binary equivalent of it, and now from this binary we have to find the decimal equivalent. So that is 2021, 22, 23, 24, 25, 26, 27, 28, 29, 210, 211. Okay, so now getting all the weights with which the multiplicative factor is 1, what we will get here, it will be 2 raised to the power 2 plus 2 raised to the power 3 plus 2 raised to the power 4 plus 2 raised to the power 5. Okay, so after 8 here it will be 2 raised to the power 7. Okay, so after 8 this one 2 raised to the power 9. Okay, and then 2 raised to the power 11. What we have to do, we have to add them. So here it will be 4 plus 8 plus 16 plus 32. Okay, so 2 raised to the power 7 is how much? So let me calculate it. 2 raised to the power 7 is 128 plus this is 512. Okay, and 2 raised to the power 11 is 2048. Now adding them together, what I will get, So let me add them. 2048 plus 512 plus 128 plus 32 plus 16 plus 8 plus 4. Okay, so what I will get here, I will get 2748. So 2748 is the decimal equivalent of my number. Okay, so that is the decimal equivalent of number. So that's it for today, in which we have seen that how to convert a 3-digit hexadecimal code to the decimal equivalent. Okay, so I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So in previous section we have seen that how to convert any hexadecimal number to its decimal equivalent. Okay, so in that video what we have done is that first we had a hexadecimal number. Okay, we have converted it to the binary one. Okay, and from a binary number what we have done, we have converted it to a decimal equivalent. Okay, so now in this question we have some decimal numbers, and from the decimal we have to find the hexadecimal equivalent of these numbers. Okay, so what will be the procedure here? So the procedure here will remain same. While here we have a decimal number, first of all we have to find the binary equivalent of it, and from the binary we have to find the hexadecimal. Okay, so the overall procedure will remain same. So here the first question we have is this 10. Okay, and we can see that the binary equivalent of it is how much. We can use this table here as well. So the binary equivalent of 10 is 1010. Okay, so the hex equivalent of it is also given here, and that is A. So that is the hex equivalent of my number 10 here. Okay, so that is in base 10, this is in base 2, and this is in base 16. Similarly we have this 15, this in base 10. So the binary equivalent of it is here. It is also given here. The binary equivalent of it is 1111. Okay, in binary, and we can see that the hex equivalent of it is also given here, and that is F16. So these are here. We have easier parts, and we have seen that how to find their equivalent here. So what we have here, this part C. So in solving part C, what we have to do, let me remove it. Okay, in solving 32, what we have to do, first we have to convert it to its binary equivalent. So in binary equivalent we will have 20, 21, 22, 23, 24, 25, 26 and 27. We have to use the sum of the products rule. So here 32, the number here is this 2 raised to the power 5 is 32. Okay, so we can write here 1, while others 1 will remain 0s. Okay, so the binary equivalent of it is this 2 raised to the power 5. So okay, so all the others will remain 0. So therefore what we have to do, we have to use here this is binary, while this is another binary. Okay, so here the 0 0 equivalent here, this is 0, while here 0 0 1 0 is equivalent to how much? That is now 2. Okay, so we can see that this is 2. So therefore the hex equivalent of this 32 is 20 in hex. Okay, so that is the hexadecimal equivalent of my number, which is 32 here, that is in decimal, while this one here we obtained is in binary. Okay, so that is the procedure by using which we can convert any decimal number to the binary equivalent. So another one here is this part D. So let me solve part D here. So in part D we can see that that is 54 in decimal. Okay, so converting it to the binary equivalent, what we have here, we have here 2 raised to the power 5 is 32. So let me write it here, 132 plus 16 is how much? That is 48, and 2 are left, so this is 1. So all others will remain 0 here. Okay, and making all other 0, what we can do here now, taking groups of 4s here, so 4 bits group will give me here, this is 00 0010. So 0010 is here equivalent to 2. Okay, so that is 2, and similarly 0011, let me see here is that 0011 is 3. Okay, so that is 3. So therefore that this was basically the binary equivalent. So from it we have obtained this number, which has given me 32 in hexadecimal. Okay, so we can see that this 32 is the hexadecimal equivalent of my number 54 in decimal. Okay, so that's it for today, in which we have discussed some very easier methods for converting decimal number to their binary equivalents, and from the binary equivalent we have seen that how to convert those binary equivalent to the hexadecimal equivalents. So that's it for today, and see you soon. Hello guys, I hope all of you will be fine. So today we are going to discuss the octal numbers. Okay, so in today's lecture we are going to convert each of the octal numbers to their decimal counterparts. Okay, so the first question here is that is 14 with the base of 8. Okay, so you must have to keep in your mind that whatever number you want to convert to the decimal number, what you have to do, you have to first separate out the digits. So the digits here are, this is the leftmost digit while this one is the rightmost. Okay, so these are the digits, and what I have to do, I have to write or multiply this number with every digit here. Okay, so let me write 8 here, this is multiplied by 8, and this is multiplied by 8. Okay, and after 8 we have to add them. What we have to do then, we have to write the powers of 8. So let me start it from 0 and then 1. Okay, so in this manner I can convert any octal number to their decimal part, or any number I will have, I can convert it to their decimal one just by writing the base and start them from the 0 to 1. Okay, so what I will get here, it will be 8 with 8 raised to the power 0 is 1. Okay, and multiplied by 4. Similarly 8 raised to the power 1 is 8 multiplied by 1. Okay, so that would be 4 plus 8. So now I will get 12 in decimal. Okay, so that is what, that is the decimal counterpart of this number. So that is the answer of part A. So in order to simplify or revise the concept here, so suppose I have a number A B here with the base of x. Okay, so let us say that this is a number in x base. So what you have to do, if you want to convert this number to its decimal counterpart, what you have to do, you should have to write this A with x. Okay, and similarly B with x, and you have to start it from 0 and to 1 up to the values where these numbers will be ended. Okay, so this will be what, this will be the decimal equivalent of this number. Okay, so that is the concept here, and I am going to use the same concept here with all these octal numbers, because here x is equal to 8. Okay, so when I will convert them here, I will get the equivalent decimal numbers. Similarly, now let me start part B of my question. So part B here is 53 with the base 8, again using the same scenario here. So 3 multiplied by base plus again the second number here is 5, or let me do it like, let me start it from the first number. So the number here is 5 and 3 with the base of 8. Okay, so that is the number. What I have to do, I have to write here 3 and here 5, okay, and multiply them with 8 plus multiply them with 8. Okay, so what I have to do, I have to start it from 0 and 1. Okay, now I can very easily see that this is a number which is mentioned here, and similarly this 3 is here, this one, while 8 is the base here. Now calculating it, what I will get, I will get 5 multiplied by 8 plus 3 multiplied by 1. Okay, so this is 40 plus 3, so this is 43, which is in decimal. So the decimal equivalent of 53 is 43, which is already mentioned here. This was basically the part 2 of my question. Now solving part 3 of my question, or part C. So now writing it in the same manner. So this is 6, this is 7 with the base of 8. Okay, now using the same method here, this will be 6, this will be 7, and multiplying them with the base here. Okay, multiply it with the base and 0 1. Okay, so now what I will get, it will be 6 multiplied by 8 plus 7 multiplied by 1. Okay, so what I will get, 8 6 48 plus 7. So here it will be 55 in the base 10. So that is the decimal equivalent of my number 67. That is part C. Now about part D here, what I will have here, in part D we have 3 numbers here, 174, okay, with the base 8. So now writing 1 7 with this green and another one with this blue. Okay, so that is a number 174, and this is in base 8. Okay, so now writing these numbers again. So 1, okay, and then 7, and the last one is 4, and multiplying them with the base here. Okay, here, and multiplying it with base here, and starting from the 0, the power of the base will start from 0, then 1, then 2. Okay, so simplifying it, what I will get here, it will be 4 multiplied by 1 plus 7 multiplied by 8, and this would be 64 multiplied by 1. Okay, so now it will be how much? 64, this is 56, and this is 4. Okay, so this will be as 56 plus 4 is 60, and this is 124 in the decimal. Okay, so in this manner, what we can do, we can convert any 3-digit octal number to their decimal counterpart. Okay, so that is the decimal equivalent of my number. Similar rule will be applied here for part E, for part F, and for part G. Let me solve it. Okay, so let me solve part G here. So for part G, what I have to do, I have to write here. Now let me start it with this red. So that is 2. Okay, the green one is 6, then 7, and the last one here will be, let me write it with this color. Okay, so that is 3. Okay, so 2 6 7 3. Now let me, and this is in octal number. Now let me convert it. So writing their values here, I will get here 2 this is 6. Okay, now blue one, this is 7, and the pinkish one is 3. Multiplying them with 8. Okay, adding them, and at the end what I have to do, I have to start writing the powers of the base. So starting from 0, 1, 2, 3. Okay, so now calculating them, what I will get, 3 multiplied by 1 plus 7 multiplied by 8 plus 6 multiplied by 64 plus this is 2 multiplied by 8 multiplied by 8 multiply 8 is how much? That is 64. 64 multiplied by 8 is, so writing them here, 8 raised to power 3 is how much? That is 512. Okay, so 512. Okay, so now adding them, what I will get, 3 plus 56 plus 64 multiplied by 6 is 64 multiplied by 6 is 384. Okay, 512 is 1024. Now adding them together, what I will get, now let me add them with plus 1024 plus 56 plus 3, so I will get here 1467. Okay, so 1467 is now in decimal, and that is the decimal equivalent of my number which is mentioned here. Okay, so these are all the steps which we have seen for the 2-digit octal number, 3-digit octal number, and at the end 4-digit octal number as well. Okay, so the same procedure will be followed for the part H. So give it a try, and you will see that this is a quite convenient method to convert an octal number to their decimal counterpart. Okay, so that's it for today. I will see you with some more questions in our upcoming video. See you soon. Welcome back, guys. So this is question number 44 of our section 2.9, and here we have to convert each of the decimal number mentioned here to their octal counterpart. Okay, so the first number here is this 23, which is in decimal. So what I have to do, I have to find a number which is in octal. Okay, so which procedure do I have to use here? So I will use the repetitive division here. So the number here I have is 23, and I have to divide it over 8. Okay, so dividing it over 8, what I will do, I will make it 8 to 16. So the difference between 23 and 16 is how much? That is 7. Okay, so that's it, because now this 2 cannot be further divided, and I have got this 27. Okay, so writing it here, I will start it from here to here. Okay, from this point to this one. So where this 2 is the most significant digit, while this is the least significant digit, so here the answer is 27 in octal. Okay, similarly for part B, where I have this 45 in decimal, and in order to convert it to its octal counterpart, what I have to do, let me use the same procedure. Okay, so writing here 45, so which number which is lower than 45 is the multiple of 8. So 8 5 40. Okay, and 5 will remain here. So this will be the remainder, while this one is the multiplicative factor which gave me 40. So here, starting it from here to here, while this one is the most significant digit, while this one is the least significant digit, so I will get 55 in octal number. Okay, welcome back, guys. This is question 45 in our section 2.9, and here what I have to do, I have to convert each octal number to their binary counterpart. Okay, so what we have to do here, we have the octal number, okay, first of all I have to convert it to the decimal number, okay, and after decimal we can very easily convert it to their binary counterparts. Okay, so let me start it from this part A. So 17 with the base 8. Now the decimal equivalent of it will be 1 multiplied by 8. Okay, similarly 7 multiplied by 8, and we have already seen that how to convert any octal number to their decimal counterpart. So writing it 0 and then 1. Okay, what I will get, 1 multiplied by 8 is 8, okay, and 7 multiplied by 8 as per 0 is 7, okay, and this will be 15 in decimal. So this is the decimal equivalent of my number, which is here. And now to convert it to their binary equivalent, what I have to do, let me write here 20, 21, 22, 23, 24, 25, 26 and 27. Okay, so now writing this is 2 raised to 4, so this is 16, so this is higher than this. So 8 plus 4 is 12, plus 2 is 14 and plus 1 is 15. Okay, so that is what, that is the binary equivalent of my number, which is now 17, and the binary equivalent of 15 is now 111. Okay, so the binary equivalent of it is 1111 in the binary. Okay, so that is the answer of part A. Similarly, now solving part B of my question, what I have to do, I have to write here, what I have to do, I have to again use the same procedure what I have used here. Okay, so for part B here I have here 26 in octal. Okay, this is in octal. Now to convert it to the decimal, what I have to do, 2 multiplied by the base plus 6 multiplied by the base, where this 2 is this one while 6 is this one which is mentioned here. Okay, so starting from 0 and then 1 here, and let me simplify it. What I will get, this is 8 multiplied by 2 is 16 plus 6 multiplied by 1, because 8 as per 0 is 1, so 1 multiplied by 6 is 6. Here I will get 22 in the decimal. Okay, so this is the decimal equivalent of my number. What I have to do now, I have to convert it to the binary, and the procedure I have been using here is basically the sum of the product rule. Okay, so 2 raised to 4 is 16. Okay, 16 plus 8 is 24, so it is not possible to make it 1, so this is 0. This is 4, so 16 plus 4 is 20, and this one is 22. So now writing this one is this one. So that is now the binary equivalent of my number. Okay, so the part B, I had 26 in the octal, while the binary equivalent of it is 10110. Okay, so that is the binary equivalent of my number. Similarly, now using the same procedure for 145 in the octal as well. Okay, so now let me use the same procedure. This is part C, and in part C I have 145 in octal. Okay, converting it to the decimal, so 1 multiplied by 8 plus 4 multiplied by 8 plus 5 multiplied by 8. Okay, starting from 0, 1 and then 2. So what I will get here, this will be 1 multiplied by 8 is 64. Okay, 4 multiplied by 8 plus 5 multiplied by 1. Okay, so here I will have 5 plus 32 plus 64. Okay, so how much would it be? So this is 32 plus 64, 96. 96 plus 4, 96 plus 5 is 101. Okay, so that is the decimal equivalent of my number. Now to find the binary equivalent of my number, this one, what I have to do, now let me write their weights here. So 2 raised to 6 is 64. Okay, this is 2 to the power 5 is 32. Okay, this is 32, this is now 4, 32, and this is now 1 is left, so this is 1. Okay, so this is now the binary equivalent of my number, which is 145. So this is part C. So the binary equivalent of 145, which is in octal, is now 0 1 1 0 0, okay, and 1 0 1. This is the binary number in my number systems. Okay, so we have solved these 3 questions, part A, part B, part C. The part D procedure I have followed here will remain same for part D, part E, and part F as well. So give it them a try, and you will see that it is quite convenient and easy method for converting any octal number to their binary counterparts. Okay, so that's it for today, and I will see you with some more questions like this one in our upcoming video. Thank you so much and see you soon. Welcome back, guys. So this is question number 46, and here I have to convert each of the binary number mentioned here to their octal counterparts. Okay, so previously we have seen that how to convert any decimal number to the octal numbers and octal number to their decimal counterparts. Similarly, we have also seen that how to convert any octal number to their binary equivalent. So here we are given the binary numbers and we have to convert them to their octal counterparts. So the procedure will remain same. Here we have all the numbers, so let me write them with this color. Here we are given the binary numbers. From binary I have to convert them directly to the decimal numbers. Okay, and from decimal I can very easily convert them to their octal counterparts. Okay, so now let me start it from part A. So in part A I have 100 in binary. Okay, converting them to the decimal, what I have to do, as I have previously told you, that what I have to do, I have to write the bits here. Okay, and I have to multiply them with the with the base here. Okay, and then adding them and start writing the powers from 0, 1 and 2. Okay, so these will remain, this will become 0 because the multiplicative index will be multiplied with this 0 here. Similarly here this will also be zeros, and here I will get 2 to 4. So the decimal equivalent of it is 4. Okay, what I have to do, I have to convert it to the octal, and we can very easily see that up to 7 all the decimal numbers are just like the octal. So the octal equivalent of it is also 4. Okay, so the binary equivalent of 4 is 100, and the octal number of it is this 4. So this is for part A. Now solving the part B of my question, what I have to do, I have to write here this 110. Okay, so this is part B, which is mentioned here 110. What I have to do, I have to write here 1. So what I will get here, it will become 2, this is 0, and here I will get 6. Okay, so as this is also less than 7, so here I will also get 6. So the equivalent of 110 is also 6 in octal. Okay, so another number here we have is 1100. Okay, so now writing here 1100, and this is part C here. So 1100, writing the equivalent of it in the decimal number, what I have to do, so let me start it here. So 0 multiplied by 2. Okay, similarly the second 0 multiplied by 2. Okay, 1 multiplied by 2. Okay, and 1 multiplied by 2 as well, and start writing the powers from the right side base. So 0, 1, 2, 3. Okay, this is 0, this is 0, this will be 4. Okay, and this will be 8. So what I will get here, I will get here 12. So that is the decimal equivalent of 1100. Okay. Now writing the octal equivalent of it, what I have to do, I have to use the repetitive division. Okay. So this is 12, this is 8. So now let me divide it over 8 and I will get 8 1. Okay, and the remainder of it will be 4. Okay, so we can see that here starting from here and here I will get 1 4. So that is 14 in the octal, because now this one is the most significant digit while this one is the least significant digit, and I have written them here. So the binary, okay, so the binary mentioned here is this one, while the octal equivalent of it is 14 8. Okay. Similarly, part D of it is 4 times 1. So writing them here, now removing them, this is D. So this is 1 1 1 1. This is what? This is in binary, and converting to the decimal counterpart, I will get it will be 15 in decimal. Okay. You may use the same procedure for the conversion which we have mentioned before, and converting it to the octal, what I have to do, I have to use the same procedure. So this is the decimal number, this is the base, and 8 1 is 15, and here the remainder is 7. Okay. So 1 7 is in octal. Okay. So the equivalent of it in octal is this one, that is 1 7. Similar procedure will also be used for the other numbers as well, which I have used here, because first of all you have to convert the binary number to the decimal, and from the decimal you can convert the number to their octal counterparts. Okay. So I think the concept is clear now, and in our upcoming video we will try to solve more examples like this one and try to clear more ambiguities in our upcoming video. Till then, take care of yourself, and I will see you soon. Hello guys, so welcome back, and today we are going to talk about the binary coded decimal, or also called the BCD. Okay, so in question number 47 we have to convert each of the following decimal numbers to the 8421 BCDs. Okay, so conventionally 8421 BCDs are usually called the BCD for simplicity. So wherever BCD is written, it means 8421 BCDs. Okay, so prior to the conversion of any decimal number to their BCD counterparts, what we have to do, we have to see that in decimal we have all the numbers from 0 1 2 3 4 5 6 7 8 and 9. Every number in the decimal is composed of the combination of the numbers between 0 and 9. Okay, so any combination here will give me the decimal number. Okay, so in order to convert these numbers to the binary coded decimals, what we have to do, we have to see the equivalent binary numbers of these 0 to 9 numbers. So suppose for 0 we have a 4-bit number which is 0 0 0 0. Okay, 0 0 0 1 for 1, 0 0 1 0 for 2. Okay, 0 0 1 1 for 3, 0 1 0 0 for 4, 0 1 0 1 for 5, 0 1 1 0 for 6, 0 1 1 1 for 7. Okay, 1 0 0 0 for 8, and 1 0 0 1 for 9. Okay, so these are all the numbers from 0 to 9, and above it we will get all the numbers which will give me the hexadecimal or more numbers. So these 4-bit numbers are basically the BCD numbers. Okay, and this is basically the decimal equivalent. Okay, so wherever I will have a decimal number, what I have to do, for each of the decimal number I have to write the equivalent code which is written here in the BCD. Okay, so suppose in the first number we have this 1 0. Okay, so in order to write the BCD equivalent of it, what we have to do, first of all we have to see that here we have 0 and 1. So first I will write the equivalent of this 0, which is now here, and this is 4 zeros. Okay, so here I have 0 0 0 0. Okay, and for this 1, what I have to do, I have to write the equivalent of it. Okay, so which is here, this 4-bit number is basically the BCD equivalent of this 1. Okay, so I will have, so let me write it with this black one. So 1 0 0 0. Okay, so these 4 are for this 0, while these 4 bits are for this 1. Okay, so basically we have converted our number to their BCD equivalent. So this is the BCD, while this is the decimal. Okay, so that is the way of converting any decimal number to their BCD equivalent. Okay, so let us see the solution of part B here. So in part B we have 1 3. Okay, so what we have to do here, we can see that we have 1 and 3. So writing the BCD equivalent of this 3, what we will have, this is here. So 0 0 1 1 is the equivalent of this 3. Okay, so this is the equivalent of this 3, while for 1, what I have to do, I have to write these 4 numbers which are equivalent, which are basically written in this equivalence table. Okay, so this is 0 0 0 1. Okay, these are 4 numbers which are here. Okay, so if we have this 13, so this 13 is in decimal, while this number, this 8-bit number, is the BCD number. Okay, so that is for part B. For part C, what we have to do is a similar procedure will be used. Let me see part D here. So for part D here, we have 21. Okay, so again we have two numbers, 2 and 1, writing the equivalent of 1 here. So that is 0 0 0 1. Okay, and the equivalent of this 2 is, this is here. Okay, this is 0 0 1 0. So 0 0 1 0. So that is the equivalent of it, and that is in BCD, while this is in decimal. Okay, so that is the way of converting my numbers to their BCD equivalent. Similarly, 36 will be converted. Okay, so let me do it here again. 36, this is part F. So 36 again. Okay, so again this is in decimal, so the equivalent of 6 is here. This is 0 1 1 0 0 1 1 0. Okay, and the equivalent of 3 is here. Okay, this is 0 0 1 0. So 0 0, sorry, this is 0 0 1 1. So 0 0 1 1. Okay, so these 3 are for, these 4 bits are for this 3, while these 4 bits are for this 6. Okay, so that is the BCD equivalent. So that's it for today, and I will see you with some more remaining questions which we have to solve here. I think most of the 2-digit numbers can be very easily converted by using the same table, but we will also talk about the 3-digit number in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So this is the remaining part of the question number 47, in which we have solved all the digits which were composed of the 2 digits and the decimal numbers which were composed of 2 digits. Okay, so today we are going to solve the 3-digit numbers, and similar approach will be used for the numbers which are higher than the 3 digits. Okay, so here we have part K, in which the number is 125, and this is in decimal, and we aim to convert it to the binary coded decimal. Okay, so the similar approach will be used, in which we have to see the equivalent of this 5 in the decimal to BCD table. So this is now here, this is 0 1 0 1. Okay, so that is 0 1 0 1, that is the equivalent of 5. Similarly, the equivalent of 2 is, this one is here, 0 0 1 0. So 0 0 1 0, okay, and the equivalent of 1 as well, this is 00 0 1, okay. So 1 0 0 0, okay. So we can very easily see that these 4 are for this 5, okay, these 4 are for this 2, and these are for this 1, okay. So here we can very easily see that this 125, which is a 3-digit number, has been converted to a 12-digit binary coded decimal, because every digit here has been converted to the 4-digit equivalent BCD code, okay. So that is what, that is the decimal, okay, and this is in binary coded decimal. So that is the conversion. Similar approach will be used for this 156, okay. This is part I here. So 156. Similarly here, the equivalent of this 6 is how much, that is here, this is 0110, okay. So 0110, okay. For 5 we have, let me write for 5, we have 0101, so 0101, okay, and for 1 we have this one, okay. So for 1, let me write here 0001, okay. So we can see that this is for 6, okay. Let me write it with this green. These 4 are for the 6, okay. These 4 are for this 5, while these 4 are for this one. So this is 156. This 156 is in decimal, while these codes are for the binary coded decimal. So similar approach will be used for the numbers which are higher than 3, and in that now in those numbers we can see that every decimal number is converted to the equivalent 4 bits BCD, okay. So every number, if you have 5 digits of the decimal number, so that would be 4 multiplied by 5, 20 bits of the BCD, and so on, okay. So if you have n digits of a decimal, it will have how much, n multiplied by 4 bits of the BCD. So that is the formula, and just putting here the number of digits in the decimal, we will get that, we will multiply that with the 4, and we will get that number of bits in our BCD, okay. So that's it for today, in which we have seen that how to convert any decimal number to their BCD equivalent, and with some more examples and with some more questions and their solutions, I will see you in our upcoming video. See you soon. Welcome back, guys. So this is a very interesting question. We have previously solved question number 47, in which we have converted each of the number here to their BCD equivalent, okay. In question 48, we are asked to convert each of the decimal number in problem 47 to straight binary, okay, and compare the number of bits required with that required for the BCD. So now we have to convert these number to their binary counterparts, and we have to see that how many number of bits will be required here in the straight binary and in the BCD, and what is the conversion, and what are the number of bits for each of the conversion here, okay. So previously we have seen that for the n digit decimal number, the number of bits required for the BCD will be 4 n, 4 multiplied by n, okay. So suppose here we have 2 digits. So how many number of bits will be required in BCD? That would be 8, because 4 multiplied by 2 is 8. Similarly, here for 3 I will have 3 multiplied by 4, so that will be 12. So that is the conversion here, and we can see that the minimum number of bits here will be 4. So here converting these number to their binary counterparts and seeing that how many number of bits will be required, let us see here. And for converting it, I am going to use the sum of products method. Okay, so in this method what I have to do, let me write here 2 0 2 1 2 2 2 3 2 4 2 5 2 6 2 7. Okay, so in order to convert this 10 into the equivalent binary number, what I have to do, I have to see that in which range does it lie. So 2 raised power 3 is 8 and this 2 raised power 4 is 16. So it lies in between them, and I have to choose here the lowest number here. So lower number here, lower limit here. So that would be 2 raised power 3. So let me write it here, this 1. Okay, and after a 2 is left, so 10 minus 8 is 2, so therefore I have to use this one. So here I will have 1 0 1 0. Okay, so this is the binary equivalent of my number 10. Okay, so in binary I have, for binary here I can see that 4 bits for binary. Okay, and here I can see that I have 2 digits, so 4 multiplied by 2 here is how much? That is 8. So 8 bits for binary coded decimal. Okay, so 4 bits for the binary and 8 bits for the BCD. So we can see that here the lower number of bits will be required for the binary conversion. Okay, similarly let us now go towards this 13. B is 13. So now let me convert it to the binary as well. So again I can see that this 8 is the lower limit. It basically shows me the lower limit here, because 2 to the power 4 is 16, which is higher than that. So 2 to the power 3, and how much is left? 5 is left, so therefore I'm using this one. So this is 4 plus 8 is 12. 12 plus 1 is 13. So again I am getting 4 bits for binary. Okay, and here for BCD we can see that here we have 2 digits, 1 and 3. So therefore 4 multiplied by n, or 4 multiplied by 2 is 8 bits for BCD. So for BCD I need 8 bits, while for the straight binary I need how much? I need basically 4 bits. So that is the conversion here. Now let us proceed toward this C. So C is 18, and converting it to the binary, what I have to do, this is 16, this is 32. So I have to choose the 16 because it basically illustrates the lower limit. So 1. Okay, this is now 2 to the power 4 is 16. So 2 is left, because 16 plus 2 will be 18. So therefore I am choosing this one. Okay, so all others will be 0 here. So 1 2 3 4 5. So 5 bits for binary for 18 in decimal. Okay, but the for BCD we can see that the total number of the digits here we have are 2, which are 1 and 8. So therefore 4 multiplied by 2 and the 8 bits will be required for the BCD here as well. Okay, so again for straight binary we need lower number of bits, which are 5. Okay, now going towards the F, because here this 21 25 will also be like this one, because these are lower than 32. Okay, so therefore the for D we will also need a 5 bits, for E we will also need 5 bits for the straight binary, while these two are the 2-digit decimal number, therefore we will need 8 bits for the BCD. While for F we have here 36. Okay, so now let me convert it here. So for 36 I can see that 2 raised power 5 is the lower limit, so this is now 1, and 2 raised power 5 is 32, so this is 32, and here let me write here, this is F and this is 36. So 32, and how much is left? 4 is left, so let me write here 4, and this is now 36, all others will be 0. Okay, so how many bits do I have here? So 0 1 2 3 4 5 6, so 6 bits are required for the 36. Okay, so 6 bits are required for 36, and again we have here 2 digits for the decimal, so the number of bits for the BCD will remain same, which are 8 bits here. So because 4 multiplied by 2 are 8. Okay, similarly here for 44 the same number of bits will be used, because this is also in between 32 and 64, so 6 bits will be used. For 57 again 6 bits will be required, while for part I, let me solve here. Okay, this is now 69. So now for 69 I can see that 2 raised power 6 is 64, while 64 possesses the lower limit here, so 64 is 1, and how much is left now? 69 minus 64 is 5, so therefore this 2 raised power 2 and this 1 and all others 0. Okay, so 1 2 3 4 5 6 7, so 7 bits are required for the 69 for straight binary, while we can again see that 6 and 9 are the 2 digits, and 4 multiplied by 2 will be the required number of bits for the BCD, so therefore it will remain same. So again we can see that for 69 as well 7 bits are required for straight binary, while 8 bits for the BCD. Okay, similarly for 98 we will see that, let me write here 98, and we will see that for 98 let me convert it to the binary as well. So this 2 raised power 7 is 128, this is 64, so 64 here, 64 plus 32 is 96. Okay, that is now 96, and 96 plus 2 is 98. Okay, so how many bits are required? So again 7 bits are required for the 98 as well. Okay, because 1 2 3 4 5 6 7 bits are required for the 98, while the same 8 bits are required for the BCD. Okay, so we can see here as well. For 128, let me write for the 128 here as well. Now for 128, what you have to do, this is the 125, what we have to do, this is 2 per 7, this is 128, this is 64, so I have to choose is 64 plus 32, 96, 96 plus 16 is how much? 96 plus 16 is 112. Okay, 112 plus 8 is 120. Okay, 120 plus 4 is 124, and then 125. Okay, so these are the number of bits for what? For 125. Okay, so 1 2 3 4 5 6 7 7 bits for the straight binary, while here we have 125, and we can see that here we have 1 2 3 digits. So therefore I have to write here 4 multiplied by 3, because n will be the number of the digits which are available in the decimal number. So therefore 12 bits will be required for converting it to the BCD. Okay, so in BCD we will need 12 bits, while in the straight binary we will need 7 bits. Okay, so that is the difference here. Now writing it for the part I here. Okay, sorry, part K here, part L here, 156 is here. Now converting it to the binary, let me write here. So now here we can see that 2 raised to the power 6 is how much, that is 64, but 2 raised to the power 7 is the 128. So I am going to select this 128. Okay, so 156 minus 128, so 28 is left now. So for selecting 28, now let me use this 16. Okay, 16 plus 128 is 144. Okay, 144 plus 8 is how much, that is 152. Okay, 152 plus 4 is 156. Okay, so that is the number. Okay, so how many bits are used here? So 1 2 3 4 5 6 7 8. So 8 bits are required for converting 156 to the straight binary, while we can see that 1 2 3 3 digits are available here in this decimal number. So therefore the number of bits here will be 4 multiplied by 3, so 12 bits will be used for the BCD, and again we can see that straight binary will consume lesser number of the bits as compared to the BCD. Okay, so that's it for today, in which we have seen that how straight binary numbers consumes lower number of bits as compared to the BCD counterparts, and in this question we have proved the same procedure. So that's it for today, and I will see you with some more examples and some more solutions in our upcoming video. Thank you so much. Welcome back, guys. So this is question number 50, in which we have to convert each of the BCD to their decimal counterpart. Okay, so that is a very important question, in which we have to convert any number to their decimal counterpart, and we have seen that here we have in decimal 0 1 2 3 4 5 6 7 8 9. Okay, so their equivalents are 0 0 0 0 0 0 0 1. Okay, 0 0 1 0 and 0 0 1 1. Similarly for 4, 0 1 0 0, for 5, 0 1 0 1, for 6, 0 1 1 0, and for 7 I will have 0 1 1 1. Okay, for 8 I will have 1 all zeros and 1 0 0 1. Okay, so apart from them, if I can see that we also have codes for the higher number as well. So because here we have a 4-bit number, and all the 4-bit number basically goes from 0 to 15. Okay, so all the numbers here will be should be from 0 to 15 for the 4 bits, but here I have only from 0 to 9. So what about the other ones? So let me write them here as well. So if I have 10 11 12 13 14 and 15. Okay, so let me write their equivalents as well. So here for 10 I will have 1 0 1 0. Okay, for 11 1 0 1 1. For 12 I will have 1 1 0 0 1 1 0 1 1110, and 15 I will have 1111. Okay, so here I have written them in red because in BCD these will be the invalid numbers. Okay, so whenever I will have these numbers, these will be the invalid number in the BCD, so therefore I have to ignore them, and whenever I will get them, I have to convert them and add 6 with them to gain the equivalency in their BCD or in decimal. Okay, so here I have the first number, which is now here 0001. Okay, so this is in BCD, and in order to convert it, what I have to write, I have to see this table, that in decimal counterpart, what is it? So this is 0001, and its equivalent is what? This is 1 in decimal. Okay, similarly for part B, I have 0110. Okay, so let me see that what is, let me first see 0110 here. So this is now here 0110, and its equivalent is 6 in decimal. So in decimal, this is this 6. Okay, so what you have to do, you have to first write the BCD to decimal or decimal to BCD conversion table, and after it you can very easily convert them here. Okay, so part C here is 1001. So let me see here, and this is now 1001. So 1001 is now equal to 9 in decimal. Okay, so that is the conversion we have seen, because all the numbers here are from A to C. These are the 4-bit numbers, and it is very easy to convert them into their equivalent by decimal numbers. So in part D we have 0001, okay, and 1000. Okay, so now we can see that this is an 8-bit number, and converting it to the decimal equivalent, what I have to do, I have to start selecting the 4-bit number from the rightmost end. So 0001 is the first 4-bit number, this 0001 is the second one. So this is 10001. Let me see that what is equal to. So that is now equal to 8. So writing 8 here, because this is now equivalent to 8, and this 0001 is, this is now 1. Okay, so this is in decimal equal to 18. Okay, so decimal equivalent of this is 18. So this is part D. Part E will remain same, part F will also will remain same. Let me solve part H here as well. So in part H I have 1001, okay, and 1000. Okay, so now here we have these 4 bits and these 4 bits, and now let me see their equivalent numbers here. So 1000 is now this 8. So this is now 8 here. Okay, and this now 1001. So this is now here 1001. This is now 9. Okay, so writing 9 here, let me write here, let me write it with this. So this is now what? This is in decimal. So this is equal to the 98. So this is part H. For part I, which is the last part of this question, let me write here. So 1 0 0 0 0. Okay, so 1 2 3 4. Okay, 1 2 3 4 1 1 1 0, and all others are also zeros. Okay, so this is basically a 12-bit number, and in converting it, let me start the same procedure. So start getting the 4 bits, 4 bits here, 4 bits here, and 4 bits here. Okay, I think I've written it wrong. Okay, so 0001. Okay, is it 1 1 2 3 4? Okay, so 1 2 3 4 5 6 9, 12, 11, 12. Okay, so let me see that. This is now 1, 2, 3, 4, 0, 0, 0, 0. Okay, these are within 4 bits, and 1, 1, 1, 0. Okay, and then 0, 0, 0 and 1. So that is the number. So now let me start getting the groups of them. So the first 4 groups is here, the second group is here, and the third group is here. Okay, so now let me see their equivalents here. So the equivalent of 0 is can be very easily see that it is here. So this is 0, this is now 0. The equivalent of 0, 1, 1, 1 is 7, which is here. So this is now 7, and this 1, 0, 0, 0 is now this 8. Okay, we can see that this is here, so this is 8. Okay, so we have converted them here. This is now this. Okay, this is here, and this one is here, and this is now in the decimal. So we can see that a 12-bit number has been converted to 3-digit decimal equivalent. Okay, so that's it for today, in which we have seen the solution of part 50 of our question, and that is the end of the binary coded decimal part, which is also a very important coded decimal numbers for our coding systems, and it has many uses. We will cover the applications of it in our upcoming videos as well. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So this is the question number 51, in which we have to convert each of the BCD numbers to their decimal counterparts. Okay, so previously we have seen that how to convert each of the BCD number to their decimal counterparts. So again, let me write them here. For it, I am selecting this white color. So here we have here, this is a decimal number. Okay, and the BCD numbers here. Okay, so we have 0. For 0 we have 0, 0, 0, 0. For 1 we have 0, 0, 0, 1. For 2 we have 0, 0, 1, 0. For 3, 0, 0, 1, 1. Okay, after 8 we have 4, and for 8 this bit will be 1, while the others will be 0. And for 5, 0, 1, 0, 1. For 6, 0, 1, 1, 0. For 7, 0, 1, 1, 1. Okay, for 8 we have 1, 0, 0, 0, and for 9 we will have 1, 0, 0, 1. Okay, so up till this limit we will have all the numbers which are included in the BCD, and their counterparts are also available in the decimal as well. Okay, after 8, whatever numbers we will get, those will be the invalid BCD numbers. And what are those numbers? So let me use this red color for it. So for those, let me have here 10, and for 10 we have 1, 0, 1, 0. For 11 we have 1, 0, 1, 1. Okay, for 12, 1, 1, 0, 0. For 13, for 15 and 14 and 15, let me write them here. It will be 1, 1, 0, 1. Okay, 1, 1, 1, 0. And for 15 we will have 1, 1, 1, 1. Okay, so all the numbers beyond this limit are the invalid BCD numbers. Okay, because their validity in the decimal numbers or in the BCD are not proved. All the numbers in the BCD will be composed of the combination of these numbers. Okay, those will be the combination of these numbers in the decimal, and writing their codes will give me the decimal numbers. Okay, so all the numbers here are basically decimal numbers. So what if we will get any numbers from this invalid decimal number? What we have to do, we have to add, okay, 6 with it, 6 with them. Okay, so in binary, what is the equivalent of 6? In binary, the equivalent of 6 is 0 1 1 0. So there we will have to add this number with it. So this is the range, and by keeping this range in mind, let me solve our part A here. So in part A we have 1 and all the zeros here. Okay, so 0 0 0 0. So now what we have 1 here. This is basically an 8-bit number. Here we have the MSB as a 1, while all the numbers here are the zeros here. So to solve it, let me write here this with red. So this is the first, these are basically the first 4 bits, while this one is the other 4 bits. Okay, so here we can see that this is what we can see very clearly, that this corresponds to the 0. So therefore in decimal this will be equal to 0. Okay, what about it? This is 1,000,000. Okay, so what is it equal to? This is, now we can see that this is now 8. So therefore writing it here as well, we will get that this is the 80 in decimal. So that is the decimal equivalent of my number, which is here in BCD. Okay, similarly part B here, let me write the part B here and using the same color here as well. So part B here, I have 1 2 3 4 5 6 7 8 9 10 11 12. This is basically a 12-bit number. Okay, so writing it here, what I will do, let me start it from this MSB. So here it will be 0 0 1 0. Okay, up to this point, then 0 0 1 1 0 0 1 1, and then 0 1 1 0 1 1 1. So you can very easily see that here how many groups do we have here. So let me start grouping them from this lower significant bit side. So these are the 4 bits. Okay, these are the 4 bits, and here these 4 bits as well. Okay, now looking into the table and writing the corresponding decimal numbers from them here, this is 0 1 1. So let me see here that where is the 0 1 1. Okay, so this is here, we can see that this is 0 1 1 and this is equal to the 7. This is 7. Similarly 0 0 1 1, 0 0 1 1 is here. Okay, and we can see that this is equal to 3, while this is 0 0 1 0 is how much? 0 0 1 0 is, this is this 2. Okay, so this one is 2 here. So now this is 237, and this is the answer of my question, that 237 is in decimal is equal to this number. Okay, so that is the solution of part A and part B. So let me remove it now. Okay, let me remove it and let me solve the part C of my question. So for part C of my question, let me write all the bits here as well. So here for part C we have 0 0 1 1 0 1 0 1 0 0, okay, and 1 1 0. So again using the same red color and start grouping them in the form of 4 bits. Here these are the 4 bits. Okay, these are again the 4 bits, and these are the last 4 bits. Writing them here, 0 1 1 0 is how much? So 0 1 1 0 is this 6. Okay, so this is now 6. Okay, writing them here, 0 1 0 0 is 0 1 0 0 is this 4. Okay, this is a 4, and 0 0 1 1 is, this is now this 3. Okay, so this is now 3. So that is the decimal equivalent of this number. For part D here, let me write the equivalent of part D. So writing it here, 0 1 and 1 2 3 4 zeros, 1 2 3 4 zeros, and then 1, and then again 4 zeros, and then 1. Okay, so this is my number. Now again let me write it in the form of the 4 bits group. So this is a first group. Similarly, this one is a second group, while this is a third group here. Okay, so now let me see their equivalents here. So this is now equal to this 1. Okay, writing it here 1. This is 0 0 1 0. So 0 0 1 0 is 2. Okay, so 0 1 0 0 is 0 1 0 0 is this 4. So this is 421, and this is again in decimal. Okay, so that is the solution of part D. So all the solutions we can see that are going very smoothly, and we are not getting any invalid BCD numbers. Okay, so now in order to check the other numbers here as well, let me remove them. And let me try part E here as well. As you can very easily see that I am looking for the invalid BCD numbers and looking for the question where I will get the invalid BCD number, and to tell you that how to convert those invalid into the valid BCD numbers. So in party we have 0 1 1 1, okay, 0 1 0 1, 0 1 0 1, okay, and 0 1 0 0, 0 1 0 0. So now we have again these 4 bits, these 4 bits, and these 4 bits here as well. So 0 1 0 0 is how much? 0 1 0 0 is this 4. Okay, this is 4. 0 1 0 1 is 0 1, that is 5. You can see that this is 5, and 0 1 1 1 is 0 1 1 is 7. So again all the numbers are the valid BCDs, and here we have this decimal number. Okay, so after let me solve the part F. So part F is also composed of all the numbers. So here again we will have, let me use this yellow color. Here it will have these 4 bits, these 4 bits, and these 4 bits as well. So here we will get, this will be 8 double zeros. Okay, so that will be in decimal. In G, what I will have, let me solve G. Okay, let me solve G here. So here I will have 1 0 0 1, okay, 0 triple 1, okay, and 1 0 0 0. Okay, so now let me group them as well again. So this is a first group, this is a second group, and this is basically the third group. So what here I will have, this is 1 0 0 1 0 0 is this 8. Okay, 0 triple 1 is this 7. Okay, and 1 0 0 1, 1 0 0 1 is this 9. So this is equal to 978, and this is in decimal. So all the numbers here are again the valid BCD numbers. Let me solve the part H here, which are basically the numbers containing the higher number of bits. Okay, so let me remove them here as well. Okay, so we have removed them, and here we can very easily see that this is the part H, and in part H we have 0 0 1, okay, 0 1 1 0, 0 1 1 0, okay, 1 0 0 0, 1 0 0, and 0011. So this is a number, and we have to first of all convert it to the groups of 4, and then we have to look into this table in order to see the equivalent of these bits. Okay, so here let me group them here as well. So this is a first group, this is a second group, the third group, and the fourth group as well. So this is 0011, this is this 3 1 000. Okay, this is 8. You can see and confirm that these are the same numbers. So 0110, so 0110 is 6. Okay, and this is 1. So 1683 is the number in decimal. Okay, so that is the equivalent of it. Now similarly the question here, so let me leave it and start solving this J. So the part J here is 0 11 00, okay, 0 11 00 11 00 again, 11 00 again, 11 00 11 00 and 111. So this is a number. Let me group them here as well. So this is a first group, this is a second group, okay, this is a third group, while this one is a fourth group. So here this one is the 0111, this is 7, 0110 is 0110, so that is the 6. Okay, 0110 is again 6, and this one is again 6. So this is a decimal number which is 6667. Okay, so that is the solution of part H, and that is the end of our question, in which we haven't found any number which is the invalid. So whenever in our next question, whenever we will have any number which is greater than 9 here, we will add this number with that number in the binary or in the BCD, and we will get the valid decimal numbers and valid BCD numbers out of that invalid number. Okay, so that's it for today, and I will see you with some more questions in our upcoming video. Till then, take care of yourself. Welcome back, guys. So this is the question number 52, in which we have to add the following BCD numbers. Okay, here we can see that whenever we will have the invalid BCD numbers, which we have seen in our previous section or in our previous question, which was question number 51, that whenever I will have the resultant number or any of the numbers which we have to add are the invalid numbers or the invalid BCD numbers. Okay, what we will have to do, I will have to add with them 0110, which is the equivalent of 6 in my decimal number. Okay, so whenever I will have those numbers, I will have to add them here with them, the 0110. Okay, so the part A of my question is 0010, and with it I have to add 0001. Okay, I have to add them. These two are the BCD numbers. So in adding them, what I will get, I can see that here I can get 01 is the, this will be the binary addition. This will be a binary addition which we have previously seen on our channel. Okay, so this will be a binary addition. So 0 plus 1 will be, let me choose this green color for it, 0 plus 1 is 1, this will be 1, 0 0 is 0, and this is 0 as well. So we can see that this is a valid binary number, because here the range of the binary numbers which will be the valid one will be from 0 0 0 0 to 1001. Okay, so that is the range of the valid BCD numbers, and we can see here from our previous question as well that this is basically the range where we will have all the valid BCD numbers, and above it or the numbers which are greater than 9 will have all the invalid BCD numbers. Okay, so therefore I have written them here as well for your convenience as well. Okay, so let me solve part V of my question here as well. So that would be 0 1 0 1. Okay, and with it I have to add 0 0 1 1. Okay, so I have to add them, and again for adding them I am using this greenish color. So 1 1 is 1 0, so therefore I have to write 0 here, and 1 will work as a carry here. So 1 plus 0 plus 1 will be 1 0, which is equivalent to 2. So again 0 here and 1 here as well as a carry. So 1 plus 1 is 2 plus 0 is again this 0 and 1, and here I will have this 1. Okay, so that is again a valid BCD numbers because it lies in between these numbers, which is the range of a valid BCD numbers. Okay, similarly now the part C of my question is 0 1 1 1. Okay, and 0 0 1 0. I have to add them, and for the result I am going to write this one. So 1 plus 0 is 1, 1 1 is 0, 1 will be carry here, 1 plus 1 will be 0 and 1 will here as well, and here it will be again 1 0 0 1. This is again within this range, so that is the valid BCD number. Okay, let me use this color for the part D as well. So 1 0 0 0. Okay, and 0 0 0 1. I have to add them, and adding them I will get what? I will get here 1 0 0 1. Okay, so this is again a valid BCD number. This is the part D of my question. Okay, similarly the part E of my question will be what? So let me write part E here. Okay, so it will be, I have to add 0 0 0 1. Okay, and 1 0 0 0. Okay, with it I have to add 0 0 0 1. Okay, and again 0 0 0 1. Okay, I have to add them. So in adding them I will see that here this is 1 0 0 1. Okay, and this is now 0, 1 will be carry here, so 1 0 0. Okay, we can see that this is the first 4-bit number, the second one, and we can very easily see that both of these basically lies in between this range. So therefore both of these are basically the valid BCD numbers. Okay, so that is the part E of my question. So let me move down here as well. Okay, so let me move down and see that what is the next number. So let me write it here. This is part F. So part F here is I have to add 0 1 1. Okay, 0 0 0 1 1 0. Okay, and 1 0 0, and with it I have to add 0 0 1 1 0 0 1 and 0 0 1. Okay, I have to add them together. So here I can see that I have to add them, and in adding them I have to use this color. So this will be 1 1 1 0. Okay, here it will be 1, this will be 0, 1 will be carried here, so this is 0, and 1 will be the carry here as well, and this is here as well. So let me group them together as well. So this is a first group, this is a second group, and we can very easily see that both of these numbers lie in between this range. Okay, so these are basically the valid BCD numbers, and we can very easily see that these are the numbers which can follow this rule. So all the other numbers will also be the valid BCD numbers because we have checked them, and the addition will follow the same rules which we have followed in this question here as well. So that's it for today, in which we have solved the part 52 of our book, and that's it for today. And if you have any question, you can ask me in the comment box. Thank you so much, and I will see you soon. So this is question number 31, in which we have to convert each pair of decimal numbers to binary and add using the 2's complement form. Okay, so where do we have to use the 2's complement? So whenever I will encounter any negative decimal number, so I have to convert that to the binary number first, and then we'll take the 2's complement, and after it I will have to add the two numbers. Okay, so in part A of my question I have to add 33 and 15. Okay, so this is what, let me have it. So 33 and 15, and adding them in the decimal form, what I will get here, I will get 8 and here 4, so that is 48 in the decimal form. So now in order to convert them to the binary form and adding them, and there we can, here we can see that we don't have any negative number here, so it is not mandatory to convert it to the 2's complement. Okay, so now here let me first write the same 2 0 2 1 2 2 2 3 2 4 5 6 and 7. Okay, so here what I have to do, this is the sum of the product method of converting any decimal number to the binary one. Okay, so 33 here will be how much? So here this one, this 2 to the power 5 is how much? This is 32. Okay, and adding with it this one, this will be 33. Okay, so all other terms will be 0 now here. Okay, so that is what, that is the 33. Okay, now 15 here will be how much? So this is 8 and this is 16. So let me write this 8 1, and after 8 plus 4 is how much? That is 12. 12 plus 2 is 14. 14 plus 1 is 15. Okay, and all other terms are here 0. Okay, so now that is the converted form of this 15. Now let me add them together. Okay, I will put the link of the sum of the product here, and similarly the method of adding two or more binary numbers will also be put it here. Okay, so now we can see here that 1 1 is 0 and 1, so this is again 0. 1 will be carry here, again here 0. 1 will be carry here. Okay, 0 again here. This one will be carry here. This is 1 1 0 0. Okay, so that is what, that is the summation of these two numbers. So let me see that how much is it in the decimal form. So we can see that this is 2 to the power 4. So 2 to the power 4 is the 2 to 4, the 2 to 4, 4 to 8, 8 to 16. Okay, so that is 16, while this one is 2 to the power 5. So this is what, this is 32. So 32 and 16 is 48. So we can very easily see that it corresponds with the answer which we had earlier found out. Okay, so that is the addition of my numbers, where both of the numbers have the same sign, and that is the positive sign. Similarly, now part B of my question, here this is 56 and 27. Okay, this is minus 27. So what I have to do, I have to add 56 and minus 27 together. So by adding them, what I will get, it is 16 minus 7 is 9, 4 2 is 29. So 29 and 27 is 56. So here I have this 29, and the sign with it is this positive sign. So what do I have to do? First of all, again using the same method, in which I have to convert them to the binary numbers. So using the same scenario here, okay, the same method here. So to 56, so for 56 I can see that 2 raised power 6 is 64, which is higher than 56. So therefore I have to use 2 raised power 5, which is 32. Okay, 32, and this 4 is 16. 16 plus 32 is 48. Now how much is left? I have 8 left, so 48 plus 8 is 56, and all the other terms will be 0 here. Okay, so I think this method is clear to you guys. Similarly, in order to find the 2's complement of 27, what I have to do, first of all I have to find out the binary equivalent of positive 27. So positive plus 27 is how much? So plus 27 here will be, I can see that 2 raised power 4 is the higher term, which is less than this, so that is 16. 16 plus 8 is 24. Okay, so 24. So after 24, how much is left? 3 are left, so therefore I will make these two 1 1, while this will be 0. Okay, so that is what, that is the binary equivalent of plus 27. Okay, so now in order to make minus 27 from it, what I have to do, first of all I have to take the ones complement of it. Okay, so the ones complement of it will be 1 1 1 0 0. Okay, 1 and then 0 0. What is this? This is the ones complement. Okay, and in order to take the 2's complement of it, what I have to do, I have to add 1 with it. Okay, so this will be then 2's complement, and adding 1 with it, what I will get, this will be 1 0 1 0 1 0 0 and 111. So what is this? This is the 2's complement equivalent of minus 27. Okay, so as we have seen that this is the required value, therefore I will remove all those values. Now let me remove them. Okay, because I have to add this value with it, and I will take this one and 1 1 1 0 0. Okay, and 1 0 1. Okay, and add them with this one. So adding them, what I will get, I will get here 1 0 1 1 1 0. 1 will be here, so 1 1 is 0. 1 will be here, so 0 here, and 1 will be here, and this one will be discarded. Okay, so what is this? This will be the answer of my question. So now let us see that whether this is 29 or not. So this one, the first one here, this is 2 raised power 4, and 2 raised power 4 is 16. Okay, plus 8. Okay, plus 4, and this is 0 plus 1. So 16 plus 8 is 24. 24 plus 4 is how much? 28 and 29. So this also corresponds with my answer, which is here, while the discarding of this one shows us that this is a positive number, because this one is also a positive number. So that is the solution of my question, which is now here. So it is clear to you guys that how I solved this one. Similarly, question C here is that in which I have to subtract this minus 46 from this 25, and what I have to do, the procedure will remain same. First of all, I will have to take the 2's complement of minus 46 and the binary equivalent of 25, and then add them together, and I will see that I will get the required quantities, and similar approach will also be followed here. Okay, so I will solve them in our upcoming video.